Deep in the heart of neutron stars exists a substance so extreme, so alien, that it could rewrite the rules of matter. Scientists call it strange matter, and it's unlike anything we've ever seen or survived. Today, we're exploring the universe's most extreme substance. Ordinary matter versus extreme matter. Imagine the world around you, every object, every living thing, even the stars above, all made of something so familiar that we rarely stop to think about it: ordinary matter. Ordinary matter is what physicists call baryonic matter, the stuff that makes up atoms, and atoms are made of three tiny building blocks: protons, neutrons, and electrons. Protons and neutrons form the nucleus, packed tightly at the center, while electrons whirl around it in clouds, zipping at speeds we can barely imagine. These particles are held together by fundamental forces, with the electromagnetic force keeping electrons orbiting nuclei, and the strong nuclear force gluing protons and neutrons together, defying the natural repulsion between positively charged protons. In this comfortable, familiar world, matter behaves predictably. Ice melts into water, wood floats in water, stars burn in steady nuclear reactions, and atoms collide, bond, and form molecules in an endless cosmic dance. But once we start crushing matter to extremes far beyond anything we experience on Earth, the rules begin to bend, the familiar order begins to break, and ordinary matter starts to behave in ways that defy intuition, revealing the strange and extreme side of the universe. And there's degenerate matter, a bizarre form of matter where the classical rules of pressure and temperature give way to the rules of quantum mechanics. Take a white dwarf, for instance, the remnant of a star like our Sun that has exhausted its nuclear fuel. When the fusion in the core ceases, the star collapses under its own gravity, squeezing the remaining matter into a dense sphere roughly the size of Earth, yet containing a mass comparable to the Sun. The pressure preventing it from collapsing further doesn't come from heat, like in ordinary gases, but from a quantum effect called electron degeneracy pressure. This is a direct consequence of the Pauli exclusion principle, a fundamental law of physics stating that no two electrons can occupy the same quantum state at the same time. Electrons resist being squashed into the same space, and their collective resistance halts the star's collapse, creating a body of matter that is unimaginably dense, yet still familiar in composition: carbon, oxygen, and other light elements. A teaspoon of white dwarf matter would weigh tons on Earth, a reminder that even ordinary elements can take on extraordinary properties under extreme compression. Push the compression further, and we move beyond white dwarfs into the realm of neutron stars, objects so extreme they challenge every instinct we have about matter. When a star with a mass greater than about 8 times that of the Sun reaches the end of its life, it explodes as a supernova, violently shedding its outer layers. The core left behind, if massive enough, collapses further, crushing protons and electrons together to form neutrons in a process called inverse beta decay. Suddenly, the star is no longer supported by electron degeneracy pressure, because the electrons have been consumed in the creation of neutrons, and what remains is a dense ball composed almost entirely of neutrons. Neutron degeneracy pressure, the quantum resistance of neutrons to being squeezed into identical states, now takes over, holding up an object with a mass greater than the Sun in a sphere only about 20 kilometers across. A neutron star is so dense that a sugar cube-sized piece would weigh 1 billion tons. A cosmic paradox where a teaspoon of matter outweighs a mountain, and the familiar world of atoms no longer exists as we know it. Neutron stars are already extreme, but even they have limits. Neutrons themselves are made of quarks, up and down quarks bound together by the strong nuclear force. The pressures inside the most massive neutron stars push these neutrons so close together that some physicists wonder if the quarks inside might start to break free, forming a new phase of matter entirely. When you squeeze neutrons together beyond the density of a neutron star, Ordinary nuclear matter might dissolve into a soup of free quarks, a state called quark matter, where the familiar distinction between protons and neutrons no longer exists. Among the quarks, something even stranger could emerge. The introduction of strange quarks into this mix could form strange matter, a substance potentially more stable than anything we know, denser than neutron star cores, and so alien that it could rewrite our understanding of what matter can be. In this context, the ordinary matter we live in, with its predictable atoms and molecules, is nothing more than a delicate, fragile structure, a veneer over a universe where the rules can be bent, twisted, and broken at cosmic scales. The journey from ordinary matter to the extreme forms of white dwarfs and neutron stars shows a remarkable transformation dictated by the laws of quantum mechanics. As gravity increases, pressure increases, and the familiar building blocks of atoms are crushed together in ways that produce states of matter never encountered on Earth. Each stage of compression reveals new physics: electrons resisting compression in white dwarfs, neutrons resisting compression in neutron stars, and potentially quarks resisting compression in the formation of strange matter. It's a universe where density isn't just a number, but a gateway to new realms of matter, where the very concept of solid or liquid breaks down under conditions that seem almost unimaginable, yet are real, tested by the extremes of stellar evolution and the relentless pull of gravity. Even as scientists model these extreme states with supercomputers and explore them through observations of pulsars and gravitational waves, the sheer scale of these densities stretches our imagination. Ordinary matter, the atoms we take for granted, the air we breathe, the stars we see twinkling at night, is astonishingly fragile in comparison. What seems solid, permanent, and unyielding is, on the cosmic stage, a delicate structure that can be compressed, transformed, and utterly altered by the extreme forces of nature. It is only when we begin to explore these extremes that we can start to understand the potential for matter to behave in ways so alien, so extreme, that even the most sophisticated human intuition struggles to comprehend it, opening the door to a universe of possibilities where the normal is just the beginning. The concept of strange matter. When we think about matter, we usually picture what we can see: the solid floor beneath our feet, the air we breathe, the stars glittering in the night sky. Everything we interact with is made of atoms, and atoms themselves are made of protons, neutrons, and electrons. Protons and neutrons are the heavyweights at the center, forming the nucleus, while electrons swarm around them, zipping in invisible clouds. But what if I told you that even these seemingly fundamental particles aren't the final frontier? That beneath protons and neutrons lies a world even stranger, denser, and more extreme than anything we can touch, see, or imagine. Welcome to the realm of quarks, and at the extreme edge of that realm, strange matter. To understand strange matter, we have to start small, smaller than an atom, smaller than a nucleus. Inside every proton and neutron lives 3 quarks, held together by the strong nuclear force, the most powerful force in the universe when it comes to binding matter at the smaller scales. In protons, you'll find 2 up quarks and 1 down quark. In neutrons, it's the opposite: 1 up quark and 2 down quarks. These quarks are constantly moving, exchanging gluons, the particles that mediate the strong force, a furious dance of energy and motion, so fast and so dense that the quarks can never be isolated under normal conditions. This is why we don't see quarks in everyday life. They are permanently confined inside protons and neutrons, locked in a quantum prison that defies escape. But quarks themselves are not all identical. In addition to the familiar up and down quarks, there are 4 others: charm, top, bottom, and strange quarks. Strange quarks are heavier than up and down quarks, carrying more mass and energy, and they behave differently when combined with others in extreme conditions. Normally, strange quarks don't appear in the matter around us because the energy required to produce them is immense, far beyond anything in ordinary stars or planets. However, under the right circumstances, where density and pressure become unimaginable, strange quarks can enter the mix, forming a new kind of matter that physicists call strange matter. Strange matter is, quite literally, what happens when quarks escape the usual constraints of nuclear structure and rearrange themselves into a denser, more stable configuration. Imagine taking the neutrons inside a neutron star and squeezing them so tightly that the individual quarks, up and down, start to merge and mingle in a new form. Then add in strange quarks, and suddenly the matter behaves differently than anything we know. It's still matter, yes, but it's a completely alien state of matter, one that challenges our understanding of density, stability, and the very structure of the atomic nucleus. Physicists have theorized that strange matter could exist in the core of the densest neutron stars, where pressures are so high that protons and neutrons are crushed to the point of breaking apart into their constituent quarks. This environment is so extreme that it pushes matter to the edge of its stability, forcing nature to find a new configuration, and strange quarks might be the key to that configuration. In other words, strange matter may not just be possible, it might be inevitable under certain cosmic conditions. Understanding strange matter begins with understanding the quarks themselves. Up quarks are the lightest of the quarks that make up ordinary matter, and down quarks are only slightly heavier. Together, they form the protons and neutrons that dominate our universe. Strange quarks, however, are significantly heavier than both up and down quarks, with a mass roughly 100 times that of an electron, a small number in human terms, but colossal at the quantum scale. This extra mass gives strange quarks unique properties. When strange quarks are incorporated into quark matter, the result can be lower energy per particle, meaning that under extreme pressure, strange matter could be more stable than ordinary nuclear matter. It's like the universe discovering a new configuration of Lego blocks that snaps together more tightly and doesn't want to fall apart. Strange matter is not just a curiosity of theory, it's a natural extension of our understanding of the strong nuclear force and quantum chromodynamics, or QCD. QCD is the theory that describes how quarks interact through gluons, governing the behavior of the strong force. In ordinary matter, the strong force confines quarks within protons and neutrons. In strange matter, the quarks are no longer confined to individual nucleons. They form a dense, almost liquid-like sea of quarks, where strange up and down quarks coexist. This quark sea behaves in ways that are radically different from any material we've encountered on Earth, a substance so dense and compact that a sugar cube-sized piece could weigh billions of tons. Physicists first seriously considered the existence of strange matter in the 1970s and 1980s. Bodmer proposed that strange quarks might make certain forms of nuclear matter more stable, and then Witten, in his famous 1984 paper, suggested that strange matter could be absolutely stable, more stable than the matter that makes up everything around us. This idea shocked the scientific community because it meant that there could be a form of matter in the universe denser and more enduring than anything we see in our laboratories, hiding in the cores of neutron stars, or possibly even travelling through space as exotic particles called Stranglets. The concept is as simple as it is radical. Take ordinary nuclear matter, subject it to pressures far beyond what a neutron star can produce, and let the up and down quarks mix with strange quarks. The resulting matter could resist decay, hold together under unimaginable forces, and display properties so extreme that our intuition about solids, liquids, and gases completely fails. Strange matter could, in theory, exist in a form that is self-bound, meaning that it doesn't need the pressure of surrounding matter to maintain its integrity. Unlike neutrons in a neutron star, which rely on gravity to stay compressed, strange matter could maintain itself, a bubble of the most extreme substance in the universe, floating freely if removed from its stellar cradle. Quarks and by extension strange matter operate in a world where energy and mass are interchangeable, and the boundaries of physics are pushed to their limits. The addition of strange quarks changes the balance of energy in the system. Up and down, quarks alone can only form stable matter under certain pressures and densities. Add strange quarks, however, and suddenly the matter can achieve a lower energy state, which is fundamentally more stable. This is why strange matter is sometimes described as a cosmic sweet spot, a configuration where matter achieves its ultimate compactness and stability, a form that ordinary atomic matter can't approach, no matter how much you compress it. The implications of this are staggering. If strange matter exists, even in small amounts, it could teach us more about the fundamental structure of the universe than any particle accelerator on Earth. It represents a bridge between nuclear physics, astrophysics, and particle physics, linking the behavior of subatomic particles to the life and death of stars. Strange matter is the endpoint of matter under compression, a reminder that the universe is capable of states so extreme that they challenge not only our technology, but our very imagination. We can also think about strange matter in terms of its potential to exist outside of stars. Physicists hypothesize that strangelets, tiny fragments of strange matter, could theoretically travel through space. While a full strange star is enormous, strangelets could range from microscopic sizes to chunks large enough to survive collisions with other matter without disintegrating. These tiny pieces, composed of up, down, and strange quarks in a dense, self-bound state, would be unlike anything we've ever encountered, possessing densities that dwarf even neutron stars at the microscopic scale. The idea that such particles could exist in cosmic rays or be ejected from the violent collisions of neutron stars adds a tangible, almost science-fictional edge to the theory, turning strange matter from an abstract concept into something that might touch our instruments, if not our everyday lives. To truly appreciate strange matter, we must abandon our everyday intuition. In our world, mass and volume have familiar relationships. A brick takes up space, water flows, and air can be compressed only so far before it resists. Strange matter exists in a universe where the rules we take for granted no longer apply. A cubic centimetre of strange matter could weigh as much as a mountain, yet be self-bound and stable. Its properties are dictated not by chemistry or atomic interactions, but by the fundamental forces acting on quarks at subatomic distances, a realm where the strong nuclear force dominates, and where gravity, impressive though it is in stars, is almost secondary in importance. It's also worth noting that the existence of strange matter would redefine our understanding of neutron stars themselves. Not all neutron stars are necessarily uniform balls of neutrons. Their cores could harbour a strange quark soup, a region where up, down, and strange quarks mix freely. Observations of pulsars, their masses, radii and rotational speeds, combined with gravitational wave signals from neutron star mergers, could hold indirect evidence for strange matter, offering astronomers a glimpse into this alien state of matter from millions of light years away. In other words, strange matter is not just a theoretical curiosity confined to physics papers. It could be a cosmic reality hiding in the densest, most violent corners of the universe, waiting to reveal itself to those who know how to look. Strange matter challenges us because it exists at the intersection of the known and the unknown. We understand the quarks, we understand the strong force, and we understand the pressures inside neutron stars. But we have never held strange matter, never seen it in a lab, never measured its properties directly. Our models predict it, our simulations explore it, and our observations hint at its potential existence. But it remains elusive, a substance at the edge of physical reality, more extreme than any material in the universe and more stable than nuclear matter under the right conditions. It is a testament to the complexity of nature, a reminder that even in a universe dominated by ordinary matter, there are realms of extreme physics that we have only begun to touch, and strange matter sits at the very heart of that frontier. Stranglets, tiny pieces of the most extreme matter. If strange matter represents a form of matter so dense and exotic that it could exist in the hearts of neutron stars, then strangelets are its tiny ambassadors, miniature fragments of this cosmic oddity that might drift through the universe. Imagine a piece of matter smaller than a grain of sand, but denser than anything on Earth, containing hundreds, thousands, or even millions of quarks packed into a volume so tiny that the laws of ordinary physics can barely describe it. Strangelets are not just theoretical curiosities. They are the natural byproducts of a universe operating at extremes, fragments that could, in principle, survive being ejected from violent stellar collisions and travel through space like microscopic bullets of cosmic history. Strangelets are composed of up, down, and strange quarks, bound together in a self-stabilizing configuration. Unlike the protons and neutrons in ordinary nuclei, which are confined and separate, the quarks in a strangelet form a dense, uniform sea, where the presence of strange quarks lowers the overall energy per particle. This makes strangelets potentially more stable than normal nuclear matter, especially under the right conditions. It's a bit like discovering that if you rearrange the pieces of a puzzle in a new way, you create a structure that not only holds together better, but is also more resistant to breaking apart. In the universe, stability is everything, and strangelets might represent a state where matter has found its most resilient form. The intriguing thing about strangelets is that they could, in theory, range in size from microscopic particles to macroscopic chunks of matter, all self-bound by the strong nuclear force. A microscopic strangelet would be too small to see, yet contain quarks in a configuration that is denser than a neutron star. A macroscopic strangelet, if it exists, could rival mountains in density and would behave in ways no ordinary matter could, resisting crushing forces, maintaining its shape, and potentially interacting with ordinary matter in unusual ways. Strangelets are the perfect bridge between the microscopic world of quantum mechanics and the macroscopic world of stars, demonstrating how exotic states of matter can exist at scales both tiny and colossal. The stability of strange matter, and by extension strangelets, comes down to the physics of quarks and the energy of the system. Ordinary nuclei are stable because of a delicate balance between the repulsion of protons due to their positive charge and the strong nuclear force holding them together. But this balance is fragile. Try to cram too many protons into a nucleus and it becomes unstable, splitting apart in radioactive decay. Neutrons alone, outside the nucleus, are unstable, decaying into protons over time. Strange matter, however, operates under a different set of rules. When strange quarks join the mix, they help redistribute the energy among the quarks, lowering the overall energy per particle. This is what physicists call the Witten hypothesis, named after Edward Witten, who suggested that under extreme pressures, matter containing strange quarks could be more stable than ordinary nuclear matter. Unlike neutrons, which need the crushing weight of a neutron star to remain bound, strange matter could, in principle, exist in a self-stable state, holding itself together without the need for an external gravitational squeeze. This potential stability is what makes strangelets so fascinating. A tiny fragment of strange matter, once formed, might persist indefinitely, surviving collisions, travelling across the universe, or even interacting with ordinary matter without decaying. It's almost as if the universe has a secret form of matter tucked away, denser, tougher, and more enduring than anything we encounter in everyday life. And because of this stability, strangelets could, in theory, provide a window into extreme physics, allowing scientists to probe the behaviour of matter under conditions that we cannot replicate on Earth. Strangelets are not just an abstract idea. They could form naturally in the universe in some of the most violent events imaginable. One scenario involves neutron star collisions, cosmic cataclysms, where two of these ultra-dense stars spiral together, smashing into one another with energies that dwarf anything we can produce in particle accelerators. In the heart of these collisions, neutron matter is compressed beyond the density of a neutron star, potentially triggering the formation of strange matter. As fragments are ejected into space, strangelets could be flung across light years, tiny relics of a stellar event so extreme that it bends the rules of physics. Another possibility is inside the cores of the heaviest neutron stars themselves. The pressures here are so enormous that neutrons are crushed together until quarks begin to roam freely, forming a quark-gluon plasma, and, if strange quarks are incorporated, a stable, strange matter core. Over time, small pieces could break off, forming strangelets that escape through stellar winds or catastrophic eruptions. Even if these strangelets are microscopic, their existence would carry profound implications. A single fragment could contain enough quarks to outmatch an equivalent volume of ordinary matter by orders of magnitude in density, turning our understanding of the universe upside down. Laboratory experiments have also attempted to produce strangelets, though so far without success. Facilities like the Relativistic Heavy Ion Collider, RRHIC, and the Large Hadron Collider, LHC, smash atomic nuclei together at near-light speeds, briefly recreating the extreme temperatures and pressures found in neutron star collisions. In these collisions, quarks are liberated from their confinement in nucleons, forming a quark-gluon plasma that mimics the early universe microseconds after the Big Bang. The hope is that, under the right conditions, some of this quark matter could cool into stable strangelets, though detecting them is a monumental challenge. They are tiny, fleeting, and rare, and their behavior is so alien that distinguishing them from ordinary debris requires extremely precise instrumentation. What makes strangelets more than just dense matter is their self-binding property. In ordinary matter, atoms are stable only because of the forces acting between them, and nuclei need electrons and external pressure to remain intact. Neutrons, for example, decay outside of nuclei. Strangelets, however, could be absolutely stable, a term physicists use to describe matter that does not decay spontaneously, regardless of its environment. This is possible because of the inclusion of strange quarks, which helps lower the energy per baryon, creating a local minimum in the energy landscape of matter itself. Essentially, once formed, strangelets don't want to fall apart, a property that distinguishes them from any form of nuclear matter we observe on Earth. This self-stability also leads to fascinating consequences. If a strangelet were to come into contact with ordinary matter under certain conditions, it could convert nearby ordinary nuclei into strange matter, a process sometimes called strange matter contagion. While this scenario has been sensationalized in science fiction and even caused public concern during early particle collider experiments, calculations suggest that in practice, the process is extremely unlikely. Nonetheless, the very possibility demonstrates how alien and powerful strange matter could be. It doesn't behave like any material we're used to. Beyond their theoretical properties, strangelets could serve as cosmic messengers, tiny probes of environments too extreme to visit. If detected in cosmic rays, they would provide direct evidence for the existence of strange matter and the processes that create it. Instruments aboard satellites, space telescopes, and cosmic ray detectors are constantly scanning for anomalies, searching for particles with unusual mass-to-charge ratios or unexpected behaviors that could signal the presence of a strangelet. These searches are painstaking and difficult, but the payoff would be enormous. A direct glimpse into the most extreme states of matter in the universe, far beyond what can be achieved in any Earth-based laboratory. The potential implications of strangelets also extend to astrophysics. Observations of unusually compact neutron stars with masses and radii that challenge conventional nuclear physics models could hint at the presence of strange matter in their cores. Similarly, the gravitational waves detected from neutron star mergers might carry subtle signatures indicating the formation or ejection of strangelets. In this way, strangelets are not just theoretical constructs, they are intimately connected to the physics of stars, the life cycles of matter, and the extreme forces shaping the cosmos. Ultimately, Stranglets challenge our intuition about matter, stability, and density. They exist at the intersection of quantum chromodynamics, astrophysics, and nuclear physics, a realm where the rules of ordinary atoms no longer apply. In a Stranglet, quarks form a stable, self-bound system, potentially surviving indefinitely, capable of traversing the cosmos and hinting at a universe richer and stranger than we imagine. They are proof that matter is not a single, fixed concept, but a spectrum, stretching from the familiar to the extreme, and that under the right conditions, the universe can craft forms of matter that are denser, more stable, and more resilient than anything on Earth. The extreme properties of strange matter. Strange matter is not just unusual, it is unimaginably dense. To grasp its density, let's start with what we know. A teaspoon of water weighs about 5 grams, and a teaspoon of iron, one of the densest ordinary elements, weighs around 50 grams. Move beyond ordinary matter to a neutron star, and that same teaspoon would weigh hundreds of millions of tons. Neutron stars themselves are already astonishing, a dense remnant of a collapsed massive star, where gravity has squeezed the matter so tightly that electrons and protons are crushed together to form neutrons. Now imagine pushing even further beyond the neutron star limit, beyond neutrons themselves, down to the level of quarks. Strange matter is theorized to exist in this extreme regime, where the quarks are no longer confined to neutrons or protons, but exist in a free, dense sea, including the heavier strange quarks alongside the up and down quarks. In this state, matter is packed so densely that a cubic centimetre, about the size of a sugar cube, could weigh as much as 1 billion tons. The strong nuclear force which normally binds quarks inside neutrons and protons now operates across a whole new scale, keeping the quark soup stable under conditions that would obliterate any ordinary matter. This density isn't just about mass, it fundamentally changes how the matter behaves. At such scales, the spacing between quarks is vanishingly small, the quantum effects dominate, and the conventional rules of chemistry and atomic physics break down. Electrons, protons, and neutrons as distinct particles cease to exist, replaced by a unified sea of quarks, where the properties of matter are dictated entirely by the interplay of the strong nuclear force, the distribution of quark types, and the balance of energy per particle. This is matter at the absolute edge, a substance so extreme that it challenges every intuition we have about the physical world. One of the most remarkable properties of strange matter is its self-stability. Ordinary matter, even the densest atomic nuclei, relies on external forces to remain bound. Atoms need the electromagnetic force to keep electrons orbiting nuclei. Nuclei themselves rely on the delicate balance of the strong force and the repulsive forces between protons. Neutrons, removed from a nucleus, decay into protons over time. Neutron stars, despite their incredible density, require gravity to maintain their structure, the immense weight of the star pressing inward to counterbalance the quantum degeneracy pressure of neutrons. Strange matter, however, could exist independently, without requiring external pressure to hold itself together. The inclusion of strange quarks lowers the energy per particle, creating a local energy minimum where the quarks prefer to remain bound in this exotic state. In other words, once strange matter is formed, it doesn't naturally want to decay into ordinary matter. It has achieved a self-sustaining stability, an alien form of persistence that makes it fundamentally different from any material we know. This self-stability also implies that stranglets, the small fragments of strange matter, could survive in isolation, drifting through space indefinitely without changing. A single microscopic stranglet could contain thousands of quarks in a configuration that simply does not unravel. Unlike ordinary atomic nuclei which can fission, decay, or be disrupted by collisions, stranglets would be resilient, holding together against forces that would obliterate normal matter. This property has profound implications for physics and astrophysics because it means that strange matter could exist outside of neutron stars, travelling through space, or possibly forming entirely new kinds of compact objects in the universe. Strange matter also behaves differently when it comes to electric charge. In ordinary matter, the number of protons dictates the overall charge of an atom, while electrons balance it to maintain neutrality. In strange matter, the presence of strange quarks alters the balance of charge. Each quark type carries a fractional electric charge. Up quarks have plus 2/3, down, and strange quarks have minus 1/3. When these quarks mix in a strangelet, the total charge can vary in ways that are unusual compared to ordinary nuclei. Some strangelets may carry a slight positive charge, others could be nearly neutral, and certain configurations might even exhibit properties unlike any known material, such as an extremely high charge-to-mass ratio. This has direct consequences for how strange matter interacts with its surroundings. A positively charged strangelet could attract electrons or deflect protons in space, while a neutral one might pass through matter almost unnoticed. The charge distribution within strange matter is also determined by quantum effects, with the strong force and electromagnetic interactions balancing each other in a dense sea of quarks. This creates a unique environment where conventional chemical reactions do not apply, and the behavior of strange matter cannot be predicted using the laws of chemistry that govern our familiar world. In addition to electric charge, strange matter could have exotic magnetic properties. The alignment of quark spins, the distribution of charges, and the extreme densities inside strange matter create conditions for magnetic fields far stronger than anything produced by ordinary materials. Consider that neutron stars themselves generate magnetic fields billions of times stronger than Earth's. In the core of a neutron star, where strange matter may form, these magnetic fields could be even more intense and complex, affecting the behavior of the matter and possibly even influencing the star's rotational dynamics or the emission of radiation. Strangelets, too, could exhibit unusual magnetic behavior. A single strangelet might carry a magnetic moment far exceeding what you would expect from its size due to the motion and spin of its constituent quarks. This could lead to interactions with electromagnetic fields in space that are entirely alien, with strangelets deflecting, accelerating, or even catalyzing processes in ways that ordinary matter cannot. The combination of high density, self-stability, and unusual electromagnetic properties makes strange matter a substance that operates on the extreme edge of physics, a form of matter that pushes the very definition of what matter can be. Another property that sets strange matter apart is its incredible resistance to compression. In ordinary matter, increasing pressure eventually overcomes atomic bonds, crushing atoms and altering their structure. Even neutron star matter, composed mostly of neutrons, has a limit. Push too hard and you risk collapsing into a black hole. Strange matter, however, is theorized to be self-bound at the quark level, meaning that it can resist compression even without gravity holding it together. The quarks inside strange matter are packed as densely as possible while remaining in a stable configuration, so applying additional pressure may not significantly change its volume. This property has consequences for the densest objects in the universe. A strange star, composed entirely of strange matter, could support itself against collapse more effectively than an ordinary neutron star, potentially reaching higher masses without forming a black hole. The compressibility of strange matter is determined by the strong nuclear force acting among quarks, a quantum mechanical effect that makes the matter nearly incompressible on macroscopic scales. It's a level of structural integrity that has no analogue in ordinary matter, making strange matter not just dense, but exceptionally robust. Strange matter is also unusual in its response to temperature. Ordinary matter changes state with heat. Solids melt into liquids. Liquids evaporate into gases. And nuclei can be disrupted at extreme temperatures. Strange matter, due to its self-binding and the way quarks interact, could withstand temperatures far exceeding those of normal atomic matter without losing its integrity. In the cores of neutron stars, temperatures can reach millions or billions of degrees, yet strange matter could remain stable, even when ejected as strangelets into space, cooled by radiation or collisions. The internal quark configuration might remain intact indefinitely, a form of matter that survives conditions that would obliterate any other substance. The extreme properties of strange matter, density, self-stability, unusual electrical and magnetic behavior, compressibility, and temperature resilience, are not just theoretical curiosities. They shape the behavior of the universe's most extreme objects. If strange matter exists in the cores of neutron stars, it affects their mass, radius, rotation, and even the gravitational waves emitted during mergers. Strangelets travelling through space could influence cosmic ray physics or act as probes of exotic conditions in distant stars. Understanding these properties allows physicists to model the behaviour of matter at extremes, bridging the gap between particle physics and astrophysics. Strange matter challenges our very notions of material reality. Ordinary matter is fragile and temporary in comparison. Atoms and nuclei decay. Atoms move and bond. And even neutron star matter is bound by gravity. Strange matter is different. It is matter pushed to its ultimate limits, self-sustaining, incredibly dense, and able to survive conditions beyond comprehension. Its extreme properties make it a substance that belongs not to Earth, but to the cores of stars, the aftermath of cosmic collisions, and perhaps the earliest moments of the universe itself, a form of matter that whispers of the immense possibilities hidden in the cosmos. Historical discovery and theoretical development. The discovery of strange matter begins in the 1970s, ideas that would challenge everything we thought we knew about matter. To understand the birth of strange matter, we have to step back to a time when physicists were just beginning to probe the fundamental building blocks of the universe, the particles beneath protons and neutrons, and the forces that bind them together. It all began with quarks. In the 1960s, physicists Murray Gell-Mann and George Zweig independently proposed that protons, neutrons, and other hadrons were not fundamental, but composed of smaller entities they called quarks. These quarks came in types or flavors, named up, down, and strange, with the strange quark standing out because of its heavier mass and unusual properties. Initially, strange quarks were just a curiosity, appearing only in exotic particles that existed fleetingly in particle accelerators. But their presence hinted at a profound possibility. If quarks could exist in isolation inside neutrons and protons, could there be a form of matter where strange quarks weren't rare anomalies, but fundamental constituents? The first serious speculation about strange matter came in the early 1970s with Alexander Bodmer, a physicist intrigued by the extreme possibilities of nuclear matter. Bodmer asked a simple but radical question. What if there existed a form of matter even more stable than ordinary nuclear matter, something made of up, down, and strange quarks? In a series of papers, he suggested that under the right conditions, ordinary matter might not be the ultimate stable configuration. There could be something denser, more resilient, a new state of matter that the universe had barely glimpsed. His work didn't immediately make headlines. After all, quarks themselves were still considered exotic. But it planted the seed for a revolution in our understanding of matter. Following Bodmer, the Japanese physicist Akihiro Teruzawa expanded the idea, proposing that high-density environments could force quarks into configurations beyond the standard protons and neutrons. Teruzawa's work was audacious, linking the abstract world of quark theory with the violent, extreme environments of astrophysics, the cause of collapsing stars, where densities are millions of times higher than anything on Earth. He speculated that under such pressures, strange quarks could emerge naturally, forming a stable quark soup that defied the ordinary distinctions between protons and neutrons. In essence, Teruzawa suggested that the universe might already be producing strange matter in the most extreme stellar environments. and that these hypothetical quark configurations could persist if conditions allowed. The concept took a monumental leap in 1984 when Edward Witten published his seminal paper, Cosmic Separation of Phases. Witten's insight was as elegant as it was radical. He proposed that strange matter could be absolutely stable, meaning that once formed, it might exist indefinitely, even outside the cores of neutron stars. Whereas Bodmer and Teruzawa had explored possibilities, Witten formalized the physics behind it, demonstrating mathematically that a mix of up, down, and strange quarks could achieve a lower energy state than ordinary nuclear matter. This meant that strange matter wasn't just exotic, it could, in principle, be the most stable form of matter in the universe. The context of the 1970s and 1980s is crucial here. Particle physics was advancing at breakneck speed. The quark model was still new, quantum chromodynamics. The theory describing the strong nuclear force that binds quarks was being refined, and experiments at accelerators were revealing the strange world of subatomic particles. Yet at the same time, astrophysicists were grappling with the mysteries of neutron stars, pulsars, and supernova remnants. It was a period of convergence, where abstract mathematical ideas met cosmic extremes, and the notion that quarks could behave differently under immense pressure began to make tangible sense. Bodmer, Teruzawa, and Witten approached the problem from slightly different angles, but they all shared a common insight. The universe, under extreme conditions, could behave in ways that challenge our everyday intuition about matter. Bodmer's early hypotheses suggested that strange quarks could lower the energy of dense matter. Teruzawa linked this to astrophysical processes, imagining quark matter forming naturally in neutron stars. Witten provided the rigorous theoretical framework, showing that strange matter could be absolutely stable. Together, their work laid the foundation for an entirely new field, the study of exotic quark matter in extreme environments. One of the key ideas that emerged during this period was the importance of quark flavors. Ordinary nuclear matter is made entirely of up and down quarks, arranged into protons and neutrons. But the strange quark, heavier and more energetic, could alter the balance of forces in dense matter. By incorporating strange quarks into the mix, theorists realized that they could lower the system's overall energy, stabilizing matter in ways that neutrons and protons alone could not. In quantum chromodynamics, the strong force binds quarks together, and the addition of a new flavor creates more ways for quarks to arrange themselves, distributing energy more efficiently. This is why strange matter could, in principle, be denser and more stable than anything we see on Earth, a substance that might exist quietly in neutron stars, or travel through the universe as strangelets. During this period, another critical aspect emerged, the relationship between density and phase transitions. Just as water can exist as ice, liquid, or vapor, depending on temperature and pressure, matter itself can undergo phase transitions depending on density. Ordinary nuclear matter is one phase. Quark matter is another. Strange matter represents a new phase entirely, one in which quarks are no longer confined to nucleons, but form a continuous sea. Bodmer, Teruzawa, and Witten all recognize that the universe might naturally allow for such a phase transition in the densest environments, and that these phases could coexist under the right conditions. It's a profound shift in perspective. What we consider stable, ordinary matter is not the ultimate form. It's just one phase in a broader landscape of possibilities. Experimental physics at the time was far from observing strange matter directly, but accelerators were providing tantalizing clues. Collisions at high energies were briefly producing particles with strange quarks, demonstrating that nature could create these exotic building blocks. While these particles decayed in fractions of a second, they validated the theoretical models and suggested that if the pressures were high enough, millions of times higher than in a lab, strange quarks could persist and combine into macroscopic matter. Theorists began to ask, could strange matter exist in neutron star cores? or even in small stable fragments called stranglets? The question was no longer purely academic. It became a real problem in nuclear physics, astrophysics, and cosmology. Bodmer's 1971 paper outlined the first systematic argument for the energetic favorability of strange quark matter, pointing out that ordinary nuclear matter might be metastable rather than absolutely stable. This means that if given the right conditions, ordinary matter could decay into a more stable configuration, strange matter. While no one had observed this decay, the theoretical implication was profound. The universe might be quietly harboring a form of matter that is fundamentally more robust than anything familiar, waiting to appear where densities are extreme. Teruzawa, in the mid-1970s, extended this by applying the principles to stellar environments, particularly neutron stars. He speculated that inside these ultra-dense remnants of massive stars, where gravity crushes matter to unimaginable densities, protons and neutrons could dissolve into quarks, and strange quarks could naturally emerge. Teruzawa's insight was to link the microcosm of particle physics with the macrocosm of astrophysics. Strange matter was not just a theoretical curiosity, it could be a cosmic reality, shaping the evolution of stars and influencing phenomena like pulsars, supernova, and gamma-ray bursts. Witten then formalized the concept in a rigorous theoretical framework, showing mathematically that strange matter could achieve a lower energy per baryon than nuclear matter, making it absolutely stable. Witten's 1984 paper, Cosmic Separation of Phases. In 1984, Edward Witten introduced a new concept in the world of theoretical physics. While quark theory and neutron stars were already fascinating, Witten introduced a perspective that transformed our understanding of matter at extreme densities. His paper, Cosmic Separation of Phases, didn't just propose a new idea. It opened a doorway into a universe where matter itself could exist in a form that defied all previous assumptions. Witten's insight began with phase transitions, a concept familiar from everyday life. Ice melting into water, water evaporating into steam. He suggested that matter on a cosmic scale could experience analogous phase transitions, but under conditions of ultra-high density and temperature. In particular, he proposed that ordinary nuclear matter could transform into strange quark matter, a state where up, down, and strange quarks form a single, stable, self-bound configuration. Unlike the phase changes we see in everyday life, this transition isn't about temperature. It's about density, pressure, and the energy per baryon. A central idea in Witten's work was that strange matter could be absolutely stable. This means that once formed, strange matter might exist indefinitely, resisting decay into ordinary nuclear matter. It's not just stable under extreme pressures like neutrons in a neutron star, but potentially stable in isolation, in tiny fragments, or even across vast distances in space. This absolutely stable property fundamentally separates strange matter from all other known forms of matter. In conventional physics, stability is fragile. Nuclei can decay. Neutrons decay outside nuclei, and neutron stars rely on gravity to maintain their structure. Strange matter, in Witten's vision, exists independently of such constraints. Witten's approach was mathematical, grounded in the framework of quantum chromodynamics, QCD. QCD describes the interactions of quarks through the strong nuclear force, which acts at incredibly short distances but with immense strength. By analysing the energy per baryon for different quark configurations, Witten showed that a mixture of up, down, and strange quarks could achieve a lower energy state than ordinary nuclear matter. This was profound. The laws of physics themselves allowed for a state of matter that could outcompete protons and neutrons in terms of stability. The presence of strange quarks reduces the Fermi energy of the system, redistributing the energy among more quark flavors and creating a configuration that is energetically favorable. He also introduced the concept of cosmic separation of phases, drawing an analogy with how early universe conditions might allow distinct forms of matter to form and coexist. In the milliseconds after the Big Bang, the universe was a seething quark-gluon plasma, dense, hot, and chaotic. Witten proposed that during cooling, some regions could have undergone a transition into strange matter, forming stable domains that persisted as the universe expanded. These domains wouldn't necessarily be enormous. They could range from microscopic stranglets to macroscopic chunks of matter, but the principle was the same. The universe itself could produce stable strange matter naturally during extreme conditions. Another striking aspect of Witten's paper was the potential for strange matter to exist in stars, a concept that would later inspire the notion of strange stars. He argued that if a neutron star reached a certain critical density, the neutrons could decompose into their constituent quarks. Once freed, strange quarks could appear spontaneously, creating a self-bound strange matter core. This idea introduced the possibility that some observed neutron stars might not be purely neutrons at all. They could be strange stars, where strange quark matter dominates the interior. This wasn't just speculative. Witten's equations provided a framework for calculating the mass-radius relationships, pressure profiles, and stability thresholds of such stars, allowing astrophysicists to link theory with observation. Witten also addressed the conditions required for strange matter to form naturally, noting that ordinary matter would not spontaneously convert under normal conditions. The key was extreme density, where quark degrees of freedom become energetically favorable. In this environment, nuclear matter could reorganize itself into a strange quark configuration, minimizing the total energy per baryon. This wasn't something that would happen in a laboratory at the time, or even today, but it provided a roadmap for understanding where and how strange matter might exist in the cosmos. The paper didn't stop at large-scale matter. Witten also hinted at microscopic fragments of strange matter, or stranglets. These would be small, self-bound clusters of up, down, and strange quarks, potentially stable across vast timescales. Unlike ordinary nuclei, which can decay through radioactive processes, stranglets might persist indefinitely, resisting decay even in isolation. Their stability would depend on the exact number of quarks, the balance of up, down, and strange flavors, and the energy distribution within the system. Detecting such stranglets, Witten noted, would be extraordinarily difficult, but their existence could provide direct evidence of absolutely stable strange matter. He further explored the implications for the early universe, suggesting that if strange matter had formed during the quark-gluon plasma phase, it could have influenced cosmic evolution. Strange matter domains might have survived cosmic expansion, traveling through space, or seeding exotic compact objects. Witten's paper hinted at a universe where strange matter isn't merely theoretical, but could be a tangible component of cosmic structure, hidden in the densest stars, or wandering silently through space as tiny, ultra-dense particles. A fascinating element of the work is how it bridged particle physics with cosmology. Witten combined the microcosmic behavior of quarks, governed by QCD, with macrocosmic phenomena like neutron stars and the early universe. He effectively created a roadmap for understanding matter at extreme scale, showing that the principles of the strong nuclear force could dictate the structure of entire stars, the behavior of high-energy cosmic collisions, and the persistence of ultra-dense matter across the cosmos. Witten's calculations also addressed energy barriers and metastability. He considered whether ordinary nuclear matter could spontaneously convert to strange matter and found that while theoretically possible, the process requires overcoming significant energy barriers. This explained why ordinary matter remains stable on Earth. The universe doesn't naturally provide the conditions necessary for conversion. Yet, in extreme astrophysical environments, such as neutron star cores or during stellar collisions, the barriers could be overcome, allowing the formation of strange quark matter. Another remarkable aspect was his attention to observable consequences. Witten suggested that strange matter could influence neutron star behavior, potentially explaining anomalies in mass, radius, or rotational properties observed in some pulsars. He also considered how gravitational waves from neutron star mergers might carry indirect evidence of strange matter formation, a concept that would only become testable decades later with the advent of advanced detectors. The elegance of Witten's framework is that it doesn't rely on untested physics. It's grounded in quantum chromodynamics, energy minimization principles, and the known properties of quarks. The novelty isn't in breaking physics laws, but in applying them in regimes that push the boundaries of density and pressure, predicting outcomes that are extreme, exotic, and, crucially, potentially observable in the universe. Witten's paper set the stage for an entire research program that continues today. Physicists have used his work to model strange stars, predict Stranglets properties, and explore the conditions under which absolutely stable strange matter could exist. His cosmic separation of phases concept remains central to understanding how exotic quark matter might form naturally, survive, and influence cosmic phenomena. The paper also inspired experiments in heavy ion colliders, where scientists attempt to recreate tiny droplets of quark-gluon plasma in the lab, searching for signs that strange matter might form under controlled conditions. The historical trajectory from Bodmer to Terazawa to Witten demonstrates a unique synergy between theoretical speculation and rigorous physics, each built upon the other. Bodmer posed the idea of more stable quark matter, Terazawa linked it to stellar environments, and Witten formalized it mathematically. Their collective work laid the foundation for decades of research into the most extreme forms of matter in the universe, and it continues to guide both theoretical and observational studies today. The 1970s and early 1980s also set the stage for future exploration. The concept of strange matter inspired generations of physicists to study quark-gluon plasmas in accelerators, model neutron star interiors with incredible computational precision, and even speculate about cosmic relics, Stranglets, travelling through the galaxy. These early theoretical developments established a framework that bridged particle physics, nuclear physics, and astrophysics, showing how ideas at the subatomic scale can have implications for the largest, most energetic objects in the universe. The collision of quarks and cosmos. The universe is a masterful laboratory, conducting experiments at scales and energies far beyond anything humanity can recreate on Earth. Somewhere between the infinitesimal world of quarks and the titanic forces shaping stars, a convergence occurred. A meeting of particle physics and astrophysics that revealed the potential existence of strange matter. It's a story of extremes, the tiniest building blocks of matter colliding and interacting in ways that dictate the evolution of the largest structures in the cosmos. At the heart of this convergence is the behavior of quarks under extreme conditions. In laboratories, physicists had already begun to study the strong nuclear force, the interaction responsible for binding quarks into protons and neutrons. The mathematics of quantum chromodynamics, QCD, revealed a universe where quarks are held together so tightly that they cannot exist freely under normal conditions. Yet when temperatures reach trillions of degrees or densities exceed anything found on Earth, quarks can break free from confinement, forming a quark-gluon plasma. Astrophysicists were observing environments that naturally achieve these extremes. The cores of neutron stars, born from the collapse of massive stars, compress matter to densities exceeding that of an atomic nucleus by several times. In such a regime, protons and neutrons cannot maintain their individual identities. They dissolve into a dense soup of quarks, interacting with one another through the strong force in ways reminiscent of the early universe, just microseconds after the Big Bang. The parallels between lab-based quark-gluon plasma experiments and the interiors of neutron stars became increasingly apparent, revealing a bridge between particle physics and the cosmos. One critical point of convergence was the emergence of strange quarks. In high-energy particle collisions, strange quarks appeared fleetingly, proving their existence and behavior under extreme conditions. Meanwhile, in neutron stars, calculations suggested that adding strange quarks to the quark soup could lower the energy of the system, stabilizing it. This realization meant that the abstract results of particle physics experiments, quarks colliding at near-light speeds, had direct implications for stars. The microscopic rules governing quarks dictated the macroscopic fate of entire celestial bodies. The convergence became particularly striking when considering neutron-star collision, events that produce energy so immense they ripple space-time itself. When two neutron stars spiral together and merge, the resulting densities and temperatures could exceed those in any laboratory experiment. In these collisions, neutron matter is crushed beyond its limits, quarks are liberated, and conditions become favourable for the formation of strange matter. Particle physicists provide the theory for quark interactions. Astrophysicists provide the extreme environment. Together, they predict outcomes that neither could achieve alone: the potential formation of strange quark cores, the ejection of strangelets, and the generation of gravitational waves that carry the signature of exotic matter. Another layer of this convergence lies in modelling the behaviour of dense matter. Particle physicists calculate the equation of state, EOS, for quark matter, the relationship between pressure, density, and energy. Astrophysicists then use this EOS to simulate neutron star structures, predicting how mass and radius relate, how rotation affects stability, and how mergers might behave. These simulations, rooted in fundamental physics, allow scientists to propose testable hypotheses. If strange matter exists in a neutron star core, it should influence the star's gravitational wave emission, cooling rate, and magnetic field behaviour. The synergy between these fields also revolutionised our understanding of compact stars. Before the integration of quark physics into astrophysics, neutron stars were viewed as dense balls of neutrons, their properties explained largely by degeneracy pressure. The introduction of quark degrees of freedom, particularly strange quarks, challenged this picture. Suddenly, neutron stars were no longer uniform. They could contain cores of strange matter, surrounded by layers of neutrons, protons, and electrons. This multi-layered structure affects everything from thermal evolution to rotational dynamics and provides a potential explanation for observational anomalies. Stars with unexpectedly small radii, extreme densities, or rapid rotation rates that would otherwise defy conventional models. High-energy collisions in particle accelerators, such as at the Relativistic Heavy Ion Collider, RHIC, and the Large Hadron Collider, LHC, became an experimental analogue for these astrophysical environments. By smashing heavy nuclei together at near-light speeds, physicists briefly recreate quark-gluon plasma, studying how quarks and gluons behave when liberated from protons and neutrons. The data from these experiments directly inform astrophysical models, providing insights into pressure, temperature, viscosity, and the likelihood of strange quark formation. In effect, particle physics experiments on Earth became a lens through which to view the interiors of stars light years away. One of the most profound implications of this convergence is the possibility of detecting strange matter indirectly. While a neutron star's core is hidden from direct observation, the star's macroscopic properties, mass, radius, cooling behaviour, rotational frequency, and gravitational wave emission, carry imprints of its internal composition. By comparing these observations with QCD-based models, scientists can infer the presence of strange quarks. For example, neutron stars with unexpectedly high mass and small radius might indicate a self-bound strange quark core. Similarly, anomalies in pulsar timing or thermal emission could point to exotic states of matter inaccessible to ordinary physics. Magnetic and electric field dynamics provide another intersection between particle physics and astrophysics. In neutron star cores, charged quarks interact under extreme magnetic fields, producing effects that influence the star's magnetosphere, radiation emission, and particle acceleration. These interactions are calculated using QCD principles, but observed in pulsar emissions and high-energy astrophysical phenomena. The microscopic behavior of quarks translates directly into phenomena spanning kilometers and emitting energy across the electromagnetic spectrum. The convergence also extends to cosmology and the early universe. Theoretical models of strange matter formation suggest that during the quark-gluon plasma phase of the Big Bang, regions of strange quark matter could have formed naturally. This parallels laboratory experiments in heavy ion collisions, where the same quark interactions are recreated on a minuscule scale. By comparing data from particle colliders with cosmological simulations, scientists can explore the possibility that strange matter existed shortly after the Big Bang and may still persist in the universe today as strangelets or exotic compact stars. Another key point is the role of degeneracy pressure in both fields. In neutron stars, electron degeneracy pressure supports white dwarfs, and neutron degeneracy pressure supports neutron stars. Particle physics reveals that once quarks are liberated, degeneracy pressure is no longer sufficient. The strong force and the flavor composition of quarks determine the matter's stability. This allows for self-bound strange matter, where pressure and density relationships are dictated by quark interactions rather than by conventional degenerate particles. It's a fundamental shift. Particle physics defines what astrophysics observes, and astrophysics provides a testing ground for particle physics principles. The study of gravitational waves further exemplifies this fusion. Neutron star mergers, detected by LIGO and Virgo, produce signals that carry the imprint of the star's internal structure. By modelling quark matter equations of state, scientists can predict subtle variations in the waveform caused by the presence of strange quark cores. This is a direct, real-time demonstration of how particle physics underpins astrophysical observation. Quarks moving at femtometer scales influence signals stretching across millions of kilometers, detectable here on Earth. Neutrino emissions from neutron stars also provide a testing ground for this convergence. The cooling rate of a neutron star depends on the composition of its core. If strange quarks are present, they alter neutrino emission rates, producing signatures different from those expected from ordinary nuclear matter. Particle physics predicts these rates based on quark interactions, while astrophysics observes them in supernova remnants and pulsars. Together, the two fields allow scientists to piece together a picture of matter in conditions otherwise inaccessible. The convergence of particle physics and astrophysics also inspired theoretical predictions of phenomena never before imagined. Strange stars, strangelets ejected during stellar collisions, and even the possibility of exotic cosmic relics formed during the early universe all arise from this interplay. Particle physics provides the rules. Astrophysics provides the extreme environment. Only together can we understand how quarks behave when subjected to pressures millions of times greater than anything on Earth, and how these behaviors scale up to influence entire stars and cosmic events. This synergy has practical implications for experiments. Knowing that extreme densities and temperatures are required to form strange matter, physicists design collider experiments to mimic these conditions on microscopic scales. The interplay between theory and observation ensures that particle physics remains relevant to astrophysical phenomena, and astrophysics gains predictive power from quantum mechanics. The two fields feed into each other, refining equations, testing hypotheses, and expanding our understanding of matter under extremes that blur the line between the infinitesimal and the cosmic. Strange stars and the hunt for strangelets. Imagine a star so dense that a teaspoon of its material would weigh billions of tons. Now imagine that this star isn't made of neutrons like a typical neutron star. It's made entirely of strange quark matter, a substance so alien it defies every rule we take for granted about matter. These are strange stars, one of the most extreme objects physicists have ever predicted, and they might already be out there, hidden in plain sight in the universe. The idea of a strange star starts with something deceptively simple. What happens if you compress matter past the neutron star limit? In a neutron star, gravity crushes protons and neutrons together until electrons and protons merge into neutrons. But at even higher densities, something stranger can happen. neutrons themselves break apart, liberating their constituent quarks. If strange quarks appear alongside up and down quarks, the resulting matter could be self-bound, stable even without gravity holding it together. This is the foundation of a strange star, a massive sphere composed entirely of quarks in a dense, uniform state. Strange stars aren't just heavier neutron stars, they're fundamentally different. For one, they are more compact, meaning their radius can be smaller for the same mass compared to a neutron star. This changes how they spin, how they radiate energy, and how they react during collisions. Observationally, this is exciting because some pulsars and neutron stars exhibit properties that traditional neutron star models struggle to explain: unusually small radii, extremely rapid rotation, or unusual cooling patterns. Strange star models can account for these anomalies, suggesting that some of the stars we've been observing might secretly be cosmic laboratories of strange matter. Another mind-bending feature of strange stars is their surface properties. Unlike neutron stars, where the outer layer is dominated by neutrons and a thin crust of ions, strange stars could have surfaces composed entirely of strange quark matter or strangelets. This alters the way radiation is emitted, from X-rays to gamma rays, potentially producing signals that differ from ordinary neutron stars. In theory, strange stars might glow differently in X-ray telescopes, and their magnetic fields could behave in unusual ways due to the internal quark dynamics. Detecting these differences is a key challenge for astronomers and a tantalizing way to spot strange matter in the universe. Now, shift from stars to the tiniest pieces, strangelets. These are microscopic chunks of strange quark matter, potentially stable across vast timescales. Unlike normal nuclei, strangelets aren't bound by gravity. They're self-contained, held together by the strong nuclear force among quarks. A strangelet the size of a sugar cube could weigh millions of tons. Because they are stable and extremely dense, strangelets could drift through space like cosmic bullets, invisible to most detection methods, yet capable of revealing the presence of strange matter if captured or observed indirectly. The stability of strangelets depends on the balance of quark flavors. Too few strange quarks, and the matter might decay back into ordinary nuclear material. Just the right mix of up, down, and strange quarks can lower the energy per baryon, making the strangelet energetically stable. This delicate balance is why strangelets are so rare, why they're not casually forming on Earth, and why they remain largely theoretical. But it also makes them cosmic time capsules, carrying information about the most extreme conditions in the universe. The production of strangelets isn't just hypothetical. During neutron star mergers, the outer layers of quark matter could be ejected into space, forming strangelets that travel across galaxies. High-energy collisions between strange stars could also produce them. These tiny relics could, in theory, reach our solar system, offering a direct way to detect strange matter. Scientists have even speculated that some unexplained cosmic ray events could be caused by strangelets passing through Earth's atmosphere. Though confirming this remains a monumental challenge, strange stars and strangelets also push the limits of physics in other ways. The density of strange matter is so extreme that conventional atomic and nuclear rules break down. Electrons, protons, and neutrons as separate entities don't exist. Everything is a sea of quarks. Electrical and magnetic properties behave differently. Compressibility is unusual, and temperature responses defy ordinary expectations. A strange star isn't just dense, it's a laboratory for testing physics at its most extreme, where the interplay of quark flavors, strong nuclear forces, and relativistic effects creates a universe unlike anything on Earth. The cosmic role of strange stars is equally fascinating. If they exist, they could explain phenomena that puzzle astronomers: extremely dense pulsars, unusual X-ray bursts, or gravitational wave signals that don't match traditional neutron star predictions. Their mergers could be sources of ultra-high energy cosmic rays or gamma ray bursts, making them active participants in shaping the energetic universe. Unlike ordinary stars, strange stars could persist as ultra-dense remnants long after ordinary matter has dissipated, silently influencing cosmic evolution. Interestingly, Stranglets could also offer insights into the early universe. Witten's cosmic separation of phases idea suggests that during the quark-gluon plasma phase of the Big Bang, some regions might have cooled into stable strange matter. Strangelets could thus be remnants from the very birth of the cosmos, wandering through space as frozen pieces of the universe's first moments. Capturing or studying such a particle would be like holding a fragment of cosmic history, giving direct evidence of matter in its most extreme state. Scientists have also modelled interactions between strangelets and ordinary matter. Because strangelets are so dense, collisions with atoms or nuclei could be dramatic, potentially converting ordinary matter into strange matter under the right conditions. This possibility, while extremely unlikely on Earth, is a vivid demonstration of how alien strange matter really is. A substance so fundamentally different that its behaviour could alter familiar matter in ways we can barely imagine. In terms of observational astrophysics, detecting strange stars or strangelets requires combining multiple tools: X-ray and gamma-ray telescopes, gravitational wave detectors, cosmic ray observatories, and sophisticated theoretical models. Astronomers search for anomalies in stellar mass-radius relationships, unusual cooling curves, or unexpected radiation spectra. Particle physicists, meanwhile, simulate quark matter behaviour under extreme pressure, providing predictions for what signals might indicate strange matter. It's a delicate dance between theory and observation, bridging the gap between microscopic quarks and cosmic-scale phenomena. Strange stars are also expected to have rapid rotation rates, faster than typical neutron stars due to their compact size and extreme density. Their crusts, if they exist, could support enormous magnetic fields, producing pulsar-like emissions, while the quark core influences rotational dynamics, potentially causing sudden glitches in rotation speed. Observing these glitches in pulsars could provide indirect evidence for strange matter, revealing the internal structure of stars that otherwise remain hidden from direct view. The potential variety of strange stars is staggering. Some could be nearly identical in mass to neutron stars, but with smaller radii, others could rotate near breakup speeds, and some might exist as ultra-dense remnants with minimal radiation, detectable only through gravitational interactions. Similarly, strangelets could range from microscopic particles to larger clumps, drifting silently through space, influencing cosmic rays, or contributing subtly to galactic matter distribution. Strange stars and strangelets serve as a testing ground for extreme physics. They force physicists to rethink the behaviour of matter at the quantum level under enormous gravitational and electromagnetic forces. They link quark theory to observable phenomena in ways that are rare in science. A direct connection between the microscopic and cosmic scales. Every model, every simulation, every potential observation offers clues about the universe's most extreme conditions and the fundamental behaviour of matter itself. Strange matter in the heart of neutron stars. Neutron stars are already extreme, and thinking about them can make your head spin. Imagine a star that once shone brightly like the sun, exhausting its fuel and collapsing under its own gravity. The core shrinks, the outer layers explode in a supernova, and what remains is a sphere only about 20 kilometres across, yet containing more mass than our Sun. The density is so insane that a teaspoon of its material would weigh around 1 billion tonnes. Every inch of a neutron star is an environment that physics barely understands. It's the kind of place where strange matter might actually form, hidden deep inside, locked away under crushing pressure and unimaginable density. Ordinary matter is made of atoms. Protons and neutrons form the nucleus. Electrons swirl around them. And the forces we learn about in school, the electromagnetic force, gravity, dominate our world. But neutron stars operate on a different level. gravity squeezes matter so tightly that atoms themselves cannot survive. Electrons are forced into protons, turning them into neutrons. The star becomes a massive ball of neutrons, a neutron degenerate soup. This is where degeneracy pressure comes in, the quantum mechanical principle that prevents identical fermions, like neutrons, from occupying the same state. It's this pressure that keeps the star from collapsing entirely into a black hole, at least temporarily. But here's where it gets stranger. Neutrons aren't fundamental particles. They're made of quarks, tiny building blocks bound together by the strong nuclear force. Each neutron contains 2 down quarks and 1 up quark. Protons have 2 up quarks and 1 down quark. These quarks are normally confined inside nucleons, but as density skyrockets in a neutron star's core, the distance between neutrons shrinks to the point where quark confinement starts to break down. The strong force is powerful, but under extreme pressure, neutrons can dissolve into a quark soup, freeing their quarks to interact directly. When this happens, the possibility of strange quarks appearing emerges. Strange quarks are heavier than up or down quarks, so they don't normally appear in ordinary matter. But at the extreme densities in neutron star cores, it becomes energetically favourable for some of the up and down quarks to convert into strange quarks. The result is strange quark matter, a self-bound ultra-dense form of matter where up, down and strange quarks coexist in a stable configuration. It's not just a small tweak to the neutron star interior, it could dominate the core entirely, forming a distinct layer or even an entire strange star if the conditions allow. Calculations suggest that the pressure at the centre of a neutron star can reach hundreds of billions of tons per square centimetre, compressing matter to densities exceeding normal nuclear density by several times. This is exactly the kind of environment that Witten, Bodmer and Terazawa theorized as being capable of forming strange matter. Inside these cores, neutrons are so tightly packed that they cannot maintain their individual identities. The quark-gluon interactions take over, forming a new phase of matter, a quark matter core, with strange quarks playing a crucial role in lowering the energy per particle. Not every neutron star will necessarily develop strange matter. The process depends on several factors: the star's mass, the exact equation of state of nuclear matter, and the density reached in the core. More massive neutron stars are more likely candidates because their gravitational compression is greater. The pressure and density in these cores might reach the threshold where the strange quark conversion is favoured. Theories suggest a continuum, from neutron stars with ordinary neutron cores, to hybrid stars with quark cores, to fully self-bound strange stars composed almost entirely of strange matter. One of the fascinating aspects is the way strange matter could alter a star's observable properties. A quark matter core would be more compact than an ordinary neutron core of the same mass. This means the star's radius could shrink slightly, increasing its density and affecting rotational dynamics. Pulsars, rotating neutron stars emitting beams of radiation, could spin faster or experience subtle glitches due to the presence of a quark core. Magnetic fields might behave differently too, influenced by the charged quarks moving in extreme conditions, producing effects detectable from light years away. Neutron stars are also incredibly hot, at least initially, with surface temperatures reaching millions of degrees. The core is even hotter during formation, allowing quarks to move more freely. Over time, as the star cools, the strange quark matter could settle into a stable configuration, self-bound and enduring. This raises the possibility that the universe already contains a population of neutron stars with strange cores, quietly spinning and radiating, with interiors radically different from the conventional picture we have from textbooks. Modelling these cores is no simple task. Particle physicists must calculate equations of state for quark matter, incorporating the effects of strong interactions, quark flavours and extreme pressure. These calculations determine how the pressure changes with density, which then informs astrophysicists about mass-radius relationships and stability limits. Hybrid stars, neutron stars with quark cores, are predicted to have mass-radius curves that deviate from purely neutron star models. Some observed pulsars with unusually high masses exceeding 2 solar masses may be hints that quark matter exists in their cores, though the evidence is still indirect. One intriguing idea is that neutron star cores could be a continuous mix of neutron matter and strange matter, forming a kind of quark-neutron hybrid. The boundary between the two phases isn't necessarily sharp. It could be a gradient, with quark density increasing toward the center. This creates a dynamic environment where neutrons and quarks interact, producing unique thermal, rotational, and magnetic behaviors. The extreme density also affects neutrino emissions, potentially accelerating cooling compared to ordinary neutron stars, which could be measured in young neutron stars or supernova remnants. Neutron star mergers are another site where strange matter might be relevant. When two neutron stars collide, densities and pressures spike even higher than in isolated stars. Quarks could be liberated across a larger volume, allowing strange matter to form more readily and potentially even be ejected into space as strangelets. These tiny, ultra-dense fragments could travel across galaxies, carrying direct evidence of quark matter formation. The combination of extreme gravity, temperature, and density in these collisions creates conditions that physicists cannot replicate on Earth, making neutron stars natural laboratories for the study of strange matter. The magnetic fields of neutron stars add another layer of complexity. Some neutron stars, called magnetars, have magnetic fields trillions of times stronger than Earth's. These fields influence the motion of charged quarks and could interact with the strange matter core in ways that alter the star's radiation and rotational properties. Particle physics predicts that quark matter in strong magnetic fields behaves differently from ordinary nuclear matter, with anisotropic pressures and modified energy distributions. Observing the effects of these fields on pulsars may provide indirect evidence of strange matter lurking inside. Even the surface of a neutron star might reveal clues. A strange star or a neutron star with a strange matter core could have a surface of self-bound quark matter or strangelets, influencing thermal emission patterns. X-ray telescopes observing cooling neutron stars may detect anomalies in the spectrum caused by the presence of quark matter, providing a window into conditions thousands of kilometers beneath the surface. The spectrum might differ subtly in color or intensity, revealing the fingerprints of strange quarks. The interplay between gravity, quantum mechanics, and quark physics in neutron stars is astonishing. Gravity compresses matter to densities where quantum rules dominate. Quarks rearrange themselves to minimize energy, and strange quarks can emerge, creating a form of matter entirely unlike anything we experience on Earth. The resulting star is no longer just a dense ball of neutrons. It's a cosmic pressure cooker, a crucible where strange matter might be forged and stabilized, hiding in plain sight. Neutron stars also challenge our understanding of mass limits. Ordinary neutron stars cannot exceed roughly 2 to 3 solar masses without collapsing into black holes. But if strange quark matter forms a self-bound core, it could allow slightly higher masses while maintaining stability, changing the landscape of observable compact objects. This affects how astronomers interpret mass measurements of pulsars, binary systems, and X-ray sources, suggesting that some unexpectedly massive stars might harbour strange matter cores. The density and pressure inside a neutron star core are so extreme that the rules governing chemistry, electricity, and magnetism are altered. Electrons are squeezed into neutrons. Quarks move in a sea dominated by strong force interactions, and strange quarks appear to reduce the overall energy of the system. The result is matter in a state that doesn't exist anywhere else, a window into physics at its most extreme. Scientists can only infer its properties indirectly through observations of radiation, gravitational effects, and rotational dynamics. The sheer exoticism of strange matter in neutron stars also makes them ideal natural laboratories for testing fundamental physics. Equations of state derived from quark interactions can predict mass-radius relations, cooling rates, rotational anomalies, and neutrino emission patterns. These predictions are compared against observational data to refine models, pushing our understanding of matter beyond what can be achieved in laboratories. The extreme densities act as a magnifying glass, revealing behaviours of quarks, strong forces, and strange matter that would be invisible at lower pressures. Smashing matter to unlock strange quarks. Imagine a machine so powerful it can recreate condition that existed only microseconds after the Big Bang. Inside a cavernous tunnel, particles are accelerated to nearly the speed of light, then smashed together with unimaginable force. For a split second, matter is obliterated, stripped down to its fundamental pieces, quarks and gluons, before it cools and recombines. This is the world of heavy ion collisions, and it's where scientists hunt for the elusive strange matter. Two of the most famous machines for this hunt are the Relativistic Heavy Ion Collider, RHIC, in New York, and the Large Hadron Collider, LHC, in Geneva. At RHIC, gold nuclei are fired at each other at near-light speed, creating tiny fireballs hotter than the centre of the Sun by trillions of degrees. At the LHC, lead ions collide with even greater energy, recreating conditions almost identical to the earliest moments of the universe. These collisions last for mere trillionths of a second, yet during that time, quarks are freed from protons and neutrons, creating a quark-gluon plasma, a primordial soup where strange quarks can appear. In a collision, the nuclei smash together and the energy density spikes. Protons and neutrons melt into their constituent quarks. Gluons, the particles that carry the strong force, dance violently, binding and unbinding quarks in chaotic motion. Temperatures soar to 4 trillion degrees, energy densities rise beyond imagination, and matter behaves like a fluid of quarks, moving collectively in waves. In this extreme chaos, strange quarks are no longer rare. The conditions favour their creation, allowing scientists to observe phenomena that would never occur in ordinary matter. One of the most fascinating outcomes of these experiments is the production of strange particles. In normal conditions, strange quarks are suppressed, they're heavy, and nature doesn't produce them easily. But in a quark-gluon plasma, strange quarks pop into existence more frequently. Scientists measure the number of strange mesons and baryons produced in collisions to detect this effect. The more strange quarks appear, the stronger the evidence that the plasma resembles the conditions where strange matter might naturally form. These experiments don't just create strange quarks, they create tiny droplets of quark matter. Some theorists suggest that under the right conditions, these droplets could be stable long enough to behave like microscopic stranglets. Imagine a particle smaller than an atom, yet denser than a neutron star. A single grain of this strangelet could weigh millions of tons if scaled up. While detecting them directly is extraordinarily difficult, their potential existence proves that strange matter isn't just theoretical. It can be produced, even if fleetingly, in our laboratories. The detectors at RHIC and LHC are marvels of technology. Layers upon layers of sensors track every particle emerging from the collision. Physicists analyze thousands of events per second, reconstructing the trajectories of quarks and gluons, measuring their energy, spin, and momentum. These experiments are like watching the first moments of the universe in slow motion, a fleeting glimpse into a world where strange quarks roam freely and ordinary matter has no meaning. One key signature that scientists look for is strangeness enhancement. In normal nuclear collisions, strange quarks are rare. But when a quark gluon plasma forms, the production of strange quarks increases dramatically. The measurement of strange baryons and mesons provides a fingerprint of this exotic state of matter. Each collision becomes a cosmic fingerprint, a snapshot of a state that might resemble the interior of a strange star. Another exciting possibility is the formation of multi-strange particles. These are particles containing more than one strange quark, like the omega baryon, which has 3 strange quarks. Multi-strange particles are rare in ordinary conditions, but appear in these extreme collisions. Their presence gives physicists clues about how quarks interact in high-density environments and hints at the stability of strange quark matter in nature. The beauty of these experiments is how they bridge the microcosm and the cosmos. On one hand, you have femtometer-scale collisions of heavy ions. On the other, you have astrophysical objects like neutron stars, where densities are billions of times higher. The physics is the same. Quarks interact through the strong force. Strange quarks reduce energy per baryon, and under extreme conditions, stable strange matter could emerge. What scientists see in a collider is a tiny echo of what might happen inside a neutron star or during a neutron-star merger. RHIC and LHC also allow scientists to explore phase transitions in matter. Just like water can freeze or boil, nuclear matter can transition from confined nucleons to deconfined quarks. The collisions provide the perfect conditions to study this transition. By analysing flow patterns, particle correlations and temperature gradients, physicists can map the boundary between ordinary nuclear matter and quark matter. This phase diagram is crucial for understanding where strange matter might exist naturally. These experiments also push the limits of our understanding of strong force interactions. In the plasma, quarks behave almost like a liquid, flowing collectively rather than moving independently. Viscosity, thermalization, and energy dissipation in the plasma are measured to understand how quarks interact under extreme conditions. Strange quarks, heavier and slower than up and down quarks, behave differently, creating subtle but measurable effects in the particle flow. Each observation informs models of neutron star cores and strange star interiors. There's also the possibility of detecting tiny strangelets escaping the collision zone. While the plasma lasts only a few trillionths of a second, fragments of strange matter could form and survive longer than ordinary particles. Physicists search for these by looking for particles with unusual charge-to-mass ratios, extreme density, or unexpected stability. Detecting a strangelet in a collider would be a monumental confirmation that strange matter is not just a cosmic curiosity, but a tangible, producible substance. Interestingly, the collisions reveal temperature and pressure effects on quark populations. At lower energies, up and down quarks dominate. At the highest energies, strange quarks are produced abundantly. By tuning collision energy, scientists can map how quark flavors emerge, giving insight into conditions needed for strange matter formation. This experimental control allows physicists to test theories that were once purely speculative, like Witten's cosmic separation of phases under controlled laboratory conditions. The experiments also illuminate how strange matter could interact with ordinary matter. Collisions create extreme density gradients and electric fields, allowing physicists to measure how quarks cluster, separate, and recombine. Strange quarks tend to stabilize multi-quark configurations, hinting at how strangelets might form naturally in neutron star mergers or in the early universe. Every data point strengthens the connection between laboratory physics and cosmic phenomena. Beyond just quark counts, scientists examine correlations between particles. How do strange quarks pair with up and down quarks? How do they flow collectively in the plasma? These patterns give insight into the internal dynamics of quark matter, shedding light on stability, density, and energy distribution. Observing these correlations helps refine theoretical models, predicting where strange matter could exist in neutron stars, supernovae, or even drifting through space as strangelets. RHIC and LHC experiments also allow comparisons across collision systems. Colliding gold nuclei versus lead nuclei, or small ions versus large ions, changes the energy density and volume of the plasma. These differences help scientists understand the thresholds for strange quark production and quark matter formation. By studying these variables, researchers can simulate conditions that may occur in neutron stars or during supernova explosions, giving a laboratory-based window into cosmic extremes. Unlike a neutron star core, where strange quark matter might exist stably for billions of years, in a collider it flickers into existence for a trillionth of a second. Yet even in this brief instant, the physics is real. Strange quarks appear, droplets of quark matter form, and the interactions reveal the principles that govern matter at its most extreme. Each collision is a glimpse into a universe that is otherwise hidden, a microcosmic mirror of the strange matter that might lurk deep in neutron stars or in fragments travelling across space. Extreme cosmic collisions and strange matter. Neutron stars are already crazy dense, but when they collide, the universe shows its wild side. These collisions are not gentle, they are cataclysmic events where gravity, density, and energy reach levels nothing on Earth can touch. When two neutron stars slam into each other, the forces involved crush matter beyond anything we've ever seen. Neutrons break down, quarks are set free, and in the chaos, strange matter can form. These collisions happen in binary systems. Two neutron stars orbit each other, spiraling closer as they radiate gravitational waves. Eventually, the orbit collapses and the stars crash together at hundreds of kilometers per second. The impact generates heat, shock waves, and pressures so extreme that the cores of the stars melt into quark matter. The dense core may stabilize as strange quark matter, a mix of up, down, and strange quarks bound together by the strong force. This is matter we can't touch on Earth, but in these collisions, it emerges naturally. Neutron star collisions don't just form strange matter, they eject it. Bits of quark matter can be blasted into space, creating strangelets, tiny nuggets of strange matter travelling at enormous speeds. These fragments might move through galaxies for millions of years, possibly landing on planets or being detected in cosmic rays. Strangelets are incredibly dense. A particle smaller than a grain of sand could weigh as much as a mountain. Scientists are still looking for them, but their potential presence changes how we think about matter in the universe. The collisions also release gravitational waves, ripples in space-time that we can detect on Earth. These waves carry a signature of the collision, including information about the star's density and internal structure. If a strange quark core forms, the gravitational wave pattern changes subtly. Observatories like LIGO and Virgo pick up these signals, and scientists can use them to infer whether strange matter exists inside neutron stars. Every detection brings us closer to seeing the unseen world of quarks. Temperature in these collisions reaches billions of degrees, far hotter than the centre of the Sun. At this heat, nuclear matter melts completely, creating a quark-gluon plasma. In this plasma, strange quarks are produced in large numbers. Up and down quarks are already present, but the extreme conditions favour the creation of strange quarks. This isn't theoretical. Particle physics experiments at RHIC and LHC have shown that strange quarks appear more readily in high-energy plasmas, and neutron star collisions are basically a cosmic-scale version of these experiments. Collisions are messy. The matter doesn't stay in one place. Shock waves travel through the merged stars, triggering turbulent flows of quark matter. The central core can collapse into a hyperdense remnant, possibly forming a black hole. But before that, the quark matter in the core can stabilize long enough to produce strangelets. The outer layers are blown away as kilonova ejecta, rich in neutrons, protons, and sometimes strange fragments. These materials are what astronomers can detect in optical, X-ray and gamma-ray wavelengths, giving clues about the collision and the matter formed inside. Supernovae are another extreme environment for strange matter. When massive stars die, their cores collapse under gravity, and the outer layers explode. The collapsing core reaches densities higher than an atomic nucleus, and neutrons pack tightly together. Some calculations suggest that strange quarks can appear during this collapse, forming strange matter in the core. If the strange matter is stable, it could survive the explosion, forming a strange star instead of a regular neutron star. The key is the balance of pressure, density, and energy, which can tip the core into a strange quark phase. During these events, the magnetic field intensifies. Neutron stars often have strong magnetic fields, and collisions amplify them even further. Strange quarks interact differently with magnetic fields than neutrons and protons. This changes the dynamics of the plasma and can affect how energy and particles are ejected. It also influences the radiation we detect, from X-rays to gamma rays. Observing these emissions helps scientists figure out what kind of matter exists in the cores of merged stars. Some collisions produce rapidly spinning remnants. When two neutron stars merge, angular momentum is conserved, causing the new object to rotate at incredible speeds. This rotation affects the stability of strange matter cores. If a quark core is present, it can influence how the star spins, potentially creating pulsar-like signals. These signals, combined with gravitational waves and electromagnetic emissions, give a multi-messenger picture of what's happening inside, offering a way to study strange matter indirectly. Simulations of these events show that density gradients are extreme. The center can reach several times the density of a normal neutron star, while the outer layers are less compressed. Strange quarks prefer high-density regions, so the core becomes a natural location for strange matter to form first. The outer ejecta may contain small fragments of strange matter, ejected at high velocities. These fragments could survive long enough to travel through space, acting as messengers of the extreme physics inside the collision. Supernova cores also produce neutrinos, tiny particles that escape almost freely. Strange matter affects neutrino production and energy spectra. In a core containing strange quarks, neutrino emission can increase or change in pattern, influencing the cooling rate of the remnant. Neutrino detectors on Earth, like Super Kamiokande, can capture some of these particles from nearby supernovae, providing indirect evidence of strange quarks deep inside collapsing stars. Collisions also explain how ultra-heavy elements form. Neutron-rich material ejected from mergers undergoes rapid neutron capture, creating gold, platinum, and other heavy elements. If strange matter is present, the dynamics of the ejection could differ slightly, affecting the distribution and velocity of these elements. Astronomers can measure this in kilonova spectra, looking for deviations that hint at exotic cores or strange matter fragments. The physics in these scenarios is extreme but consistent. Quarks behave according to strong force rules. Under the pressures and densities of mergers or collapsing cores, strange quarks reduce the overall energy, stabilize the core, and create matter unlike anything on Earth. Each collision, each supernova, each kilonova becomes a natural laboratory where the universe tests the limits of matter. High-resolution simulations show that strangelets could survive the chaos. Tiny nuggets ejected from the central core might travel at significant fractions of the speed of light. They are stable because strange matter is self-bound. Ordinary matter can't disrupt them easily. Detecting one would be monumental, cosmic rays passing through Earth could carry them. Space probes might capture them. They could exist right now, invisible, carrying direct evidence of strange matter from some distant cosmic cataclysm. Collisions also produce jets of energy. Some neutron star mergers emit gamma-ray bursts, extremely short, but incredibly intense flashes of energy. The nature of the matter in the core, whether ordinary or strange, can affect the jet's properties, duration, and direction. Observing these bursts gives clues about the internal state of the merging stars. Multi-messenger astronomy, combining gravitational waves, gamma rays, and neutrinos, allows scientists to reconstruct what happened inside, including whether strange matter was involved. In these environments, pressure, density, temperature, and magnetic fields combine to produce conditions where strange matter is most likely to exist. Unlike Earth-based experiments, where strange quarks appear fleetingly, neutron star mergers and supernovae provide natural conditions for longer-lasting strange matter formation. The stars themselves act as colossal labs, testing theories about quark behaviour and strange matter stability. Some models suggest that strange matter could form a shell around a collapsing core. As the core densifies, quarks rearrange, strange quarks appear, and the outer layers remain mostly neutron matter. This layered structure could influence the dynamics of ejected material, the energy of gravitational waves, and the neutrino flux. Observing these effects in real events gives scientists indirect evidence of where strange matter exists in the universe. Exotic astrophysical scenarios also include neutron star black hole mergers. When a neutron star is torn apart by a black hole, the compression is extreme. Quark matter could form as the neutron star is shredded. The ejected matter may include strangelets, while the remaining material falls into the black hole. These collisions are harder to observe directly, but gravitational wave patterns provide hints of the internal physics, including possible strange matter formation. The combination of neutron star mergers, supernova cores, and black hole interactions creates a spectrum of environments. Each has slightly different densities, pressures, and temperatures, producing strange matter in different ways. Some produce stable cores, others eject fragments, and some may only produce transient quark-gluon plasma. Studying all these events together allows scientists to understand the full range of exotic matter possibilities in the universe. The biggest advantage of these astrophysical scenarios is scale. Colliders can recreate quark-gluon plasma for a trillionth of a second. Neutron star mergers sustain extreme densities for seconds, supernova cores for milliseconds to minutes. This longer timescale allows quarks to interact, strange quarks to form, and strange matter to stabilize, even if only temporarily. Observing the aftermath, ejected matter, radiation, gravitational waves, gives a window into processes that would otherwise be completely inaccessible. Neutrino emissions, gamma-ray bursts, kilonovae, gravitational waves, and strangelets all act as messengers. Each carries information about what happened inside the collision or explosion. By combining these signals, astronomers and physicists can infer the presence of strange matter, its distribution, and its behaviour under extreme conditions. Each observation is like reading a secret code written in the most extreme physics imaginable. Traces of strange matter in the universe. Astronomers have been studying neutron stars for decades, and some of what they see doesn't make sense. Pulsars spin faster or slower than models predict. Some stars are smaller than expected, others heavier. Certain neutron stars cool unusually fast, while others emit radiation patterns that don't match standard physics. Each of these anomalies is a potential sign that something stranger than ordinary matter exists inside. The first hint comes from mass and radius measurements. Neutron stars are expected to follow specific mass-radius relationships based on the equation of state of nuclear matter. Most stars fall within the predicted range, but a few exceed it. Some pulsars have masses over 2 solar masses, yet appear smaller than expected. Standard neutron star models struggle to explain this combination. Strange matter provides a solution. A core of strange quark matter is denser and more compact, allowing a star to have more mass without increasing its radius. Observing these outliers gives scientists clues that strange matter might be at work inside. Another signal is pulsar glitches. Pulsars are spinning neutron stars emitting beams of radiation like cosmic lighthouses. Their rotation is normally steady, but occasionally they jump or glitch. These sudden changes in rotation could be caused by shifts in the internal structure of the star. If the star contains strange matter, the behaviour of the quark core interacting with the outer layers could trigger these glitches. The way the star responds to rotational stress provides indirect evidence of the exotic matter inside. Cooling patterns are also revealing. Young neutron stars cool by emitting neutrinos. Strange matter changes this process. Quark matter allows faster neutrino emission, accelerating cooling compared to a neutron-only core. Observatories measuring surface temperatures of young neutron stars sometimes find stars cooler than expected. These temperature anomalies hint at an internal quark phase, possibly including strange quarks. Studying the cooling rates over years allows scientists to test models of strange matter in real astrophysical objects. Some pulsars show unusual X-ray and gamma-ray emissions. Radiation from the surface depends on the star's composition. A strange matter surface or strangelets on the crust could produce emission patterns different from standard models. Certain X-ray pulsars appear brighter or dimmer than their size and temperature suggest. Gamma-ray bursts from magnetars also show irregularities in timing and intensity. These deviations can point to a quark matter core or strange matter influencing the star's magnetic and thermal behaviour. Gravitational wave observations are another avenue. The collisions of neutron stars produce ripples in space-time. The exact waveform depends on the density and internal structure of the stars. If one or both stars contain strange matter, the signal will differ subtly from predictions based on ordinary nuclear matter. Scientists compare observed gravitational waves to models to infer the presence of quark matter. The merger events detected in the past few years already provide data that could hint at strange cores in extreme cases. Strangelets might also reach Earth as cosmic messengers. High-energy collisions in space, neutron star mergers, or supernovae could eject stable chunks of strange matter. If one of these strangelets enters the solar system, it would have extraordinary properties: ultra-high density, unusual charge-to-mass ratios, and the ability to pass through normal matter almost unhindered. Detectors designed to capture cosmic rays could identify these anomalies, providing direct evidence of strange matter travelling across the galaxy. Unusual cosmic rays have been detected that don't fit standard models. Some are heavier than expected. Others interact with detectors in strange ways. While none have been definitively identified as strangelets, the possibility exists. Each anomalous detection is examined for signals like high density, abnormal charge, or extreme energy signatures that could point to a fragment of strange matter from a distant collision or merger. The properties of magnetars also hint at strange matter. These neutron stars have magnetic fields trillions of times stronger than Earth's. The behaviour of their magnetic fields, including sudden flares and bursts, could be influenced by quark matter in the core. Strange quarks interact differently with magnetic fields than neutrons, potentially affecting the star's rotation and emission patterns. Observing magnetar activity helps scientists test whether strange matter could exist in these extreme magnetic environments. Pulsar timing arrays also provide insight. By tracking the rotation of hundreds of pulsars across the galaxy, astronomers can detect minute irregularities. Some of these anomalies could result from the presence of a strange matter core, which affects the star's internal rigidity and response to rotational stress. Even tiny deviations in spin can give clues about exotic matter inside the star. The chemical composition of ejected material in mergers offers another clue. Heavy element formation occurs in neutron star collisions, but the presence of strange matter could influence the velocity, density, and distribution of the ejecta. Observing kilonovae and their spectra allows scientists to compare predictions with models of ordinary matter and quark matter. Deviations may indicate the influence of strange cores or fragments of strange matter. Neutrino detectors also provide indirect evidence. Strange matter changes the rate and energy spectrum of neutrinos emitted during supernovae or mergers. Observatories like Super Kamiokande can capture some of these neutrinos, allowing scientists to infer extreme internal conditions. Strange matter cores produce slightly different neutrino signatures than ordinary neutron cores, and over multiple observations, patterns can emerge that hint at its presence. The combination of all these signals creates a multi-layered puzzle: mass radius anomalies, cooling rates, pulsar glitches, radiation patterns, gravitational waves, cosmic rays, magnetar activity, kilonova ejecta, and neutrino fluxes all provide pieces of evidence. While no single observation proves strange matter exists, the pattern of anomalies across multiple data sets strengthens the case. Scientists cross-check these signals, using them to refine models of how strange matter behaves in real astrophysical settings. Even the search for stable strangelets in the lab connects to these observations. Collisions at RHIC and LHC produce conditions similar to neutron star mergers. If strangelets exist in cosmic events, reproducing them, even briefly, in particle accelerators validates theories about their stability and behaviour. Experimental and observational evidence complement each other, linking Earth-based physics to cosmic phenomena. Some observed neutron stars are so unusual that standard nuclear models cannot explain them. For example, certain high-mass pulsars have smaller radii than expected. Their rotation and emission patterns also deviate from predictions. These outliers are prime candidates for hosting strange matter cores. Observing more of these stars and comparing their properties helps scientists narrow down which stars might contain exotic matter. Strange quarks change the energy per baryon, affect stability, and alter how matter behaves under extreme conditions. Observing their effects in stars, mergers, or cosmic rays allows scientists to study physics beyond what can be recreated on Earth. Every anomaly in a pulsar, every unusual gravitational wave, every strange cosmic ray could be a clue pointing to matter that is denser, more stable, and stranger than anything in our everyday world. The physics behind strange matter's extremes. At the heart of matter, beneath atoms, protons, and neutrons, there is a world stranger than anything we can see. It is a world of quarks and gluons, the building blocks of everything in the universe. These tiny particles obey rules that sound like science fiction, but are real physics. They are governed by quantum chromodynamics, or QCD for short, the theory that explains how quarks stick together, how they move, and how strange matter becomes so extreme. Quarks come in different types or flavors. The most familiar are the up and down quarks, which make up protons and neutrons. Then there is the strange quark, heavier than up and down, less common in ordinary matter. Quarks carry something called color charge, which is nothing like real colors. Instead, it is a property that governs the strong force, the strongest force in the universe, responsible for holding quarks together. Gluons are the particles that carry this force, acting like sticky glue between quarks, binding them into protons, neutrons, and ultimately into the nuclei of atoms. The strong force is incredibly powerful. It's thousands of times stronger than the electromagnetic force that holds electrons in orbit around nuclei. At short distances, it grows weaker, but at larger distances, it becomes stronger, pulling quarks back if they try to escape. This property is called confinement, and it's why we never see free quarks under normal conditions. They are trapped inside particles, invisible to the naked eye, yet forming the foundation of everything. Under extreme conditions, however, confinement can break down. In the cores of neutron stars or in high-energy collisions, quarks can move freely in a quark-gluon plasma, a fluid of quarks and gluons. This plasma is where strange quarks can appear in large numbers. The presence of strange quarks lowers the total energy of the system, which is why strange matter can be more stable under these extreme pressures and densities. In other words, strange matter is not just dense, it is energetically favoured to exist in these conditions. Density is where strange matter truly becomes extreme. Ordinary matter is mostly empty space. Atoms are tiny nuclei surrounded by clouds of electrons. Even inside a nucleus, protons and neutrons are mostly empty space, and quarks are tiny points inside them. Neutron stars crush matter to remove that empty space. Protons and neutrons dissolve into quarks, and strange matter compresses this already dense soup even further. A sugar cube-sized amount of strange matter would weigh as much as a mountain. Its density is far beyond anything experienced on Earth, surpassing even that of atomic nuclei. Quarks inside strange matter are packed as tightly as possible without collapsing into a black hole. Up, down, and strange quarks mix in a sea of gluons. The strong force binds them so tightly that the matter becomes self-contained. Unlike a neutron star core, which relies on degeneracy pressure to hold itself up, strange matter holds itself together through quark interactions. This self-binding is one of the reasons it is considered absolutely stable in theory. The Pauli exclusion principle also plays a role. Quarks, like electrons and neutrons, are fermions, which means no two quarks of the same type can occupy the same state. Adding strange quarks introduces new states for quarks to occupy, which lowers the overall energy per particle. This is why strange matter could be more stable than ordinary nuclear matter when pressures are extreme. It's not just denser, it's energetically more favourable. The mathematics of QCD is complex, but the intuition is simple. Quarks want to minimise energy. If up and down quarks alone are crowded together, the system has higher energy. Introducing strange quarks spreads the load, allowing the matter to compress further and stabilise. This is the reason why strange matter could exist as a stable, ultra-dense form of matter, unlike anything found on Earth. Colour charge creates another interesting property. In ordinary matter, colour charges cancel out inside protons and neutrons, making the particle colour neutral overall. In strange matter, quarks are mixed in a way that maintains colour neutrality but allows a much denser packing. Gluons act as mediators, holding quarks in place, constantly exchanging energy, and keeping the matter cohesive. This balance between confinement and free movement in the plasma state is one of the keys to understanding why strange matter can be so extreme. Pressure inside strange matter is unlike anything we experience. In a neutron star core, pressures reach hundreds of billions of tons per square centimetre. In strange matter, this pressure is balanced by the strong interactions among quarks. The quark-gluon interactions themselves provide structural integrity. This is why strange matter does not collapse under its own weight, yet remains thousands of times denser than ordinary matter. Temperature can also play a role. High temperatures in collisions or newly formed neutron stars allow quarks to move freely, creating quark-gluon plasma. As the system cools, strange quarks can settle into a stable configuration. This cooling process allows strange matter to remain bound and extremely dense. In theory, a chunk of strange matter could exist for billions of years without decaying, forming strange stars or tiny fragments called stranglets. Strange matter's extreme density also affects its electrical properties. Unlike ordinary matter, where electrons orbit nuclei, strange matter is mostly quarks. Some quarks carry electric charge, and their movement can create unusual electrical and magnetic behaviours. This could explain some anomalies observed in neutron star emissions or magnetic field behaviour. The strong interactions dominate over electromagnetic interactions, creating a matter that behaves unlike anything on Earth. Gravity interacts differently with strange matter too. Because it is so dense, its gravitational field is extremely strong for its size. A tiny piece of strange matter could warp space around it noticeably. Yet it is not a black hole. It is extreme, yes, but still obeys the rules of particle physics, not the singularities of general relativity. Its stability comes from internal quark dynamics, not gravity alone. Quark interactions in strange matter are also affected by flavor equilibrium. Up, down, and strange quarks adjust their numbers to minimize total energy. If there are too many up or down quarks, strange quarks are created through weak interactions. This balance is critical for stability. Unlike ordinary nuclear matter, which relies on neutrons and protons, strange matter's composition is flexible and self-adjusting, giving it extreme resilience. The formation of strange matter is a competition between pressure, energy, and density. At lower densities, ordinary nuclear matter is favoured. At extreme densities, quark matter with strange quarks becomes favourable. The transition from neutron matter to strange matter is a phase change, like water turning to ice, but far more extreme. This transition can occur in the cores of neutron stars or in high-energy collisions, wherever quarks are packed tightly enough. Scientists study these extremes by combining theory and observation. QCD predicts the behaviour of quarks, gluons, and strange quarks. Observations of neutron stars, mergers, and gravitational waves provide real-world constraints. Together, they form a picture of strange matter as ultra-dense, self-bound, quark-rich and stable under extreme conditions. Experiments at RHIC and LHC also inform this understanding. By creating quark-gluon plasma, scientists can observe strange quarks forming and interacting. These tiny, fleeting droplets mimic the early stages of strange matter formation, giving insight into its properties. Even though collider experiments last fractions of a second, the physics is the same as in neutron star cores. Strange matter is extreme in ways we can measure. Its density surpasses nuclear matter, it is self-bound by the strong force, it has unique electrical and magnetic properties, and it can exist stably under conditions that would destroy ordinary matter. It is the densest form of matter outside a black hole, yet governed by quantum chromodynamics, not singularities. Every property, from quark composition to pressure to stability, makes strange matter an extreme alien form of the universe's material. Self-binding and the strange power to spread. Strange matter is unlike anything we know. Ordinary matter needs support to stay together. Atoms are held by electromagnetic forces. Neutrons in a nucleus are held by the strong force, and stars like neutron stars are held up by degeneracy pressure. Strange matter doesn't need help. It's self-bound, held together by the strong force itself, the same force that binds quarks inside protons and neutrons. In strange matter, this force is so strong and organized that it can keep quarks together even under extreme conditions. Inside strange matter, up, down, and strange quarks mix in a dense soup. The strong force carried by gluons keeps them trapped. Unlike a neutron star, which relies on gravity and degeneracy pressure to maintain structure, strange matter holds itself. No outside pressure is required. A chunk of strange matter would keep its shape, resist compression, and survive conditions that would crush ordinary nuclear matter. This self-binding makes strange matter one of the most extreme substances in the universe. Self-binding also allows strange matter to exist in tiny fragments. Even a piece smaller than a grain of sand can remain stable. These fragments are called stranglets. Their stability doesn't depend on external forces. They are held together by internal quark interactions. Up and down, quarks alone would not form a stable particle of that size, but adding strange quarks allows more energy states, spreading out quarks and lowering the total energy. The result is an extremely dense, stable object. This property has dramatic implications. Strange matter can survive ejection from neutron star mergers, supernova cores, or high-energy collisions. Unlike ordinary matter, which would disperse, strange matter can travel through space intact. A strangelet ejected from a collision could drift across galaxies, maintaining its density and stability for millions of years. Its internal structure is self-contained and incredibly resilient. Strange matter has another remarkable feature. Under the right conditions, it could convert ordinary matter into strange matter. This is not science fiction. It's a theoretical possibility grounded in physics. If a chunk of strange matter contacts ordinary nuclear matter, the strong force may favour rearranging neutrons and protons into quarks, with strange quarks, creating more strange matter. The process spreads like a chain reaction. The key is that strange matter is energetically more stable under extreme conditions, so ordinary matter is tempted to reorganize itself into the strange state. Scientists sometimes compare this to the Ice-9 concept from literature, but carefully. Ice-9 is fictional. It freezes water on contact. Strange matter is different. It doesn't automatically transform ordinary matter in every situation. The conversion requires extreme pressure, density, or high-energy conditions, like those inside neutron stars or during collisions. In these environments, a single nugget of strange matter could trigger a transformation locally, converting nearby nuclear matter into the strange phase. The physics behind this conversion comes from energy per baryon. Ordinary nuclear matter has a certain energy density, and strange matter has lower energy per baryon under high pressure. When nuclear matter touches strange matter in this environment, quarks rearrange to reach the lower energy state. The result is a denser, more stable configuration. It's like a puzzle snapping into a more compact form. The process could propagate outward, forming new strange matter. Strangelets themselves are small but extremely dangerous in theory. A microscopic particle could weigh as much as a mountain, and its density is off the charts. The strong force inside keeps it stable, and it could interact with ordinary matter in unusual ways. If one were captured in a high-density environment, it could theoretically grow, absorbing nearby nuclear matter and extending the strange phase. Laboratory experiments search for these particles carefully, but so far they remain elusive. The self-binding property also explains why strange stars could exist. A strange star is like a neutron star, but its core is composed of strange matter. Gravity alone isn't holding it up. The quark interactions are doing the work. This allows strange stars to reach higher densities without collapsing into black holes. The crust of the star may be ordinary nuclear matter, but the core is a self-bound, ultra-dense quark soup. Its density is extreme, far beyond any laboratory experiment. Temperature influences the stability of strange matter. High temperatures, like those in mergers or supernovae, can free quarks and allow the strange phase to form. As the matter cools, the quarks settle into stable configurations. Strange matter is less likely to decay or disperse compared to ordinary matter because the internal binding is stronger than forces that would normally break apart nuclei. Cooling freezes the quarks in place, maintaining the extreme density and stability. The strong force in strange matter is not uniform. Quarks constantly exchange gluons, creating a dynamic balance. Up, down, and strange quarks adjust their numbers to minimize total energy. If there are too many up or down quarks, weak interactions convert some into strange quarks. This self-regulation keeps the matter stable. It's like a self-correcting system, maintaining its extreme density and resisting decay. Strange matter also reacts differently to magnetic and electric fields. Ordinary matter conducts electricity in familiar ways, but strange quarks create new behavior. A strangelet may carry an unusual charge distribution or interact weakly with electrons. This means that strange matter in neutron stars or ejected into space could have electromagnetic effects unlike ordinary matter. Observing these effects in pulsars, magnetars, or cosmic rays could provide clues to its presence. Gravity interacts with strange matter in extreme ways. A tiny strangelet could warp space-time noticeably because of its density, though it is not a black hole. In strange stars, gravity works with the self-binding of quarks. The star can resist collapse even at densities far higher than neutron stars. This makes strange matter unique. It is extreme, but still governed by particle physics, not singularities. The self-binding also defines the shape and size of strangelets. Unlike normal nuclei, which have limits to how large they can grow before becoming unstable, strange matter fragments can remain small, medium, or large, while staying cohesive. Each quark interacts with others in a balance, creating a compact object with a smooth surface at the quark level. These objects could range from tiny subatomic chunks to macroscopic lumps, all bound by the same principles. The potential to convert ordinary matter is fascinating, but it has limits. Conversion requires direct contact in high-pressure environments. Isolated strangelets in low-density space won't spontaneously convert nearby matter. The reaction spreads only where conditions allow, such as in the interior of a neutron star or during a high-energy collision. In theory, a strange star could grow its strange matter core by slowly converting ordinary neutrons under immense pressure. Laboratory experiments at RHIC and LHC hint at the principles behind self-binding. When quark-gluon plasma forms, strange quarks appear more frequently. Tiny droplets of quark matter, perhaps proto-strangelets, can persist briefly. The physics observed in these experiments mirrors what happens in astrophysical environments, but at a tiny scale. It confirms that quarks can form self-bound systems under the right conditions. The idea of strange matter spreading through contact also ties into energy considerations. Every quark in a strangelet is in a lower energy configuration than it would be in ordinary nuclear matter. This means that converting ordinary matter into strange matter is energetically favourable where pressure and density are high. The process is self-sustaining under those conditions, creating a chain reaction until the environment can no longer support conversion. The extreme density, self-binding and conversion potential of strange matter define its place in the universe. It is denser than atomic nuclei, stable under enormous pressure, resilient against decay, and capable of influencing its surroundings in unique ways. Its interactions with ordinary matter, electromagnetic fields, and gravity are all altered by its quark composition. These properties make strange matter one of the most extreme forms of material known, with behaviour that challenges our intuition about matter, stability, and density. Strange matter's self-binding also affects star evolution. If a neutron star's core converts to strange matter, the star's structure changes. The core becomes denser, more stable, and potentially smaller in radius. This could affect the star's rotation, magnetic field, and emission patterns. Observers on Earth can detect these changes through pulsar timing, X-ray emissions, and gravitational waves, providing indirect evidence of the self-binding properties at work deep inside the star. Even in collisions, Self-binding governs outcomes. During a neutron star merger, fragments of matter are ejected violently. Strangelets, due to self-binding, can survive the violent forces that would shred ordinary nuclear matter. These surviving fragments could travel through space for millions of years, potentially reaching planets, stars, or interstellar detectors. Each fragment is a durable witness to extreme quark interactions. Strange matter versus black holes. Extreme but different. Strange matter is one of the most extreme substances in the universe, denser than anything in normal physics. Yet it is not a black hole. Both are extreme, both bend reality in ways our brains struggle to grasp. But the difference lies in how they hold themselves together and what happens inside. Black holes are defined by gravity. Strange matter is defined by quarks and the strong force. Black holes form when matter collapses under its own gravity beyond a critical point. Once the event horizon forms, not even light can escape. The matter inside is compressed into a singularity, a point of infinite density. No physics we know can describe the singularity itself. It is a breakdown of our equations. Strange matter, on the other hand, is extreme but still governed by particle physics. Quarks interact with gluons. Flavor equilibrium is maintained and density reaches incredible levels, but it does not collapse into a singularity. A chunk of strange matter is tangible, describable, and theoretically measurable. The density comparison is astonishing. Ordinary atomic nuclei have densities around 2 to 3 times 10 to the 17th power kilograms per cubic meter. Neutron stars compress matter further, up to 5 times 10 to the 17th power kilograms per cubic meter. Strange matter exceeds even that, packing quarks tightly enough that a sugar cube-sized piece would weigh millions of tons. A black hole's singularity, by contrast, has infinite density at its core. But the rest of the black hole, the event horizon, is empty. Strange matter is dense throughout its volume, not just at a point. Gravity behaves differently around the two. Black holes warp space-time to the extreme. Strange matter produces gravity according to its mass and density. But space-time remains continuous. No event horizon forms. A star made entirely of strange matter could exist without collapsing into a black hole if its mass is below the critical limit. Its density can be higher than neutron stars without producing singularities, because the quark interactions provide the internal pressure necessary to resist gravitational collapse. Strange matter also interacts with its surroundings in ways black holes cannot. It can emit radiation, support magnetic fields, and participate in nuclear reactions in surrounding layers. Black holes, by contrast, absorb everything crossing the event horizon, and their observable behavior is limited to the accretion disk and jets. Strange matter stars, or strangelets in space, can radiate, interact electromagnetically, and even convert nearby ordinary matter under extreme conditions. Black holes do none of that. They are purely gravitational phenomena. Temperature plays a role in both, but differently. A black hole has Hawking radiation, which is tiny for massive black holes and increases only as mass decreases. Strange matter can exist at billions of degrees in newly formed stars or during collisions, yet remain stable because the strong force binds quarks together. Its internal energy doesn't require gravity to hold it in place. In essence, strange matter has internal structure, while a black hole's interior is a mathematical singularity without definable layers. Rotation also sets them apart. Black holes can spin, creating frame-dragging effects that twist space-time. Strange matter stars can rotate rapidly too, but their rotation is constrained by physical rigidity. The quark interactions provide self-bound cohesion, allowing rotation without breaking apart. In black holes, rotation affects the shape of the event horizon and the ergosphere, but there is no material to deform. Strange matter can be extremely dense, spin fast, and still have tangible structure. Electromagnetic fields are another distinction. Strange matter carries charge distribution depending on quark composition. Magnetic fields can be generated and maintained, especially in strange stars, where rotation and quark alignment produce pulsar-like phenomena. Black holes can have magnetic fields only through interaction with charged plasma outside the event horizon. Inside, there is nothing. Strange matter exists inside its own field, while black holes interact externally. The pressure inside a black hole is essentially undefined at the singularity. Strange matter pressure, however, is extreme but measurable. Quarks exchange gluons constantly, adjusting to maintain stability. The strong force counters compression naturally. Even if you compress a chunk of strange matter beyond the density of a neutron star, it resists further collapse through quark interactions until gravity overwhelms it. A black hole cannot resist. Collapse is inevitable. Another difference is stability over time. Strange matter is stable under high pressure, potentially lasting billions of years, if isolated. A black hole, meanwhile, changes as it radiates Hawking radiation, albeit extremely slowly for massive ones. Strange matter can persist as a self-contained, extreme object. Black holes are extreme, but defined entirely by mass, charge, and spin, with no internal physics to measure directly. Collisions highlight contrasts as well. If a neutron star containing strange matter merges with another neutron star, the resulting object might remain a strange star or collapse into a black hole, depending on mass. The quark interactions delay collapse, provide pressure, and allow extraordinary densities without forming a singularity immediately. A black hole formed from two merging neutron stars has no such internal resistance. It collapses under gravity, producing a singularity almost instantly. Strange matter also behaves differently in terms of observable signatures. Pulsars and magnetars, if containing strange matter, produce radiation, glitches, and gravitational waves that can be measured. Black holes produce gravitational waves in mergers, but the interior is hidden. Strange matter is extreme and observable through multiple messengers: radiation, gravitational waves, neutrinos, and possibly strangelets. Black holes reveal themselves only indirectly through effects on surrounding matter and space-time. Energy per particle is another key distinction. In strange matter, the energy per baryon is lower than in ordinary nuclear matter under high pressure, which makes it stable. This self-stability is intrinsic. Black holes have no such internal measure. Their stability comes from gravity, and any interaction with other matter is dictated by the event horizon. Strange matter's self-binding makes it extreme on its own, whereas black holes rely on their environment to demonstrate extremity. The size of strange matter objects can vary widely. Tiny strangelets may exist in cosmic rays. Strange stars can have radii similar to neutron stars, but with higher density. Black holes have size defined by their event horizon radius, proportional to mass. The diversity of strange matter objects, small, medium, massive, offers a richer spectrum of physical possibilities than black holes, which are limited to mass, spin, and charge. Temperature, pressure, and magnetic field interactions make strange matter behave dynamically. Heat and rotation can produce phase changes inside strange stars, creating layers of quark matter with differing strange quark content. These layers influence emissions, pulsar glitches, and cooling rates. Black holes, by contrast, have no internal layers, and their structure is singular and uniform beyond the event horizon. Even gravity waves are distinct. Merging strange matter stars produce waveforms slightly different from merging neutron stars. The extreme density and quark interactions alter tidal deformability, affecting gravitational wave patterns. Black hole mergers have their own signature, dominated by mass and spin, with no internal structure affecting the waveform. Strange matter mergers are messy, rich with physics. Black hole mergers are cleaner in terms of what can be measured. Electrically, strange matter could interact with charged particles in ways black holes cannot. Strangelets might deflect or attract charged cosmic rays. Strange stars could support magnetospheres that produce pulsar emissions. Black holes only affect charged particles indirectly, through accretion disks or jets. Strange matter is extreme and interactive, while black holes are extreme and isolating. Even the way strange matter reacts to collisions sets it apart. Two chunks of strange matter might merge, forming a larger stable object without collapsing into a singularity, because quark interactions absorb the pressure. Two black holes merging immediately produce a new black hole. The interior physics is irrelevant, because the singularity absorbs all structure. Strange matter's extremity comes from physical forces acting inside. Black holes' extremity comes purely from gravity. Self-binding is central to this distinction. In strange matter, the strong force binds quarks together, resisting collapse and maintaining structure. Black holes have no self-binding. The gravitational pull dictates structure, leaving no room for internal physics. The strong force in strange matter allows extreme density without crossing the point of no return, unlike black holes, which are defined by crossing that point. Temperature, pressure, electromagnetic effects, rotation and stability combine to make strange matter extreme but fundamentally different from black holes. Density is off the charts. Energy per baryon is lower than ordinary matter. It can self-bind, carry magnetic fields, rotate, radiate and even propagate into space as strangelets. Black holes are extreme, yes, but they are a point of no return, a region where physics breaks down and matter as we know it ceases to exist. Strange matter exists in the universe as a kind of bridge between ordinary matter and black holes. It is extreme, self-contained, and interactive. Its limits are set by quark physics, not gravity alone. Its properties, density, stability, electromagnetic behavior, pressure, make it a candidate for the most extreme non-singular form of matter. Black holes remain singular and defined by mass, but strange matter thrives in extremes, tangible and measurable, offering insights into the fundamental physics of the universe. Chasing strange matter in the lab and beyond. Laboratories like CERN in Switzerland, the Relativistic Heavy Ion Collider, RHIC, in New York, and the Large Hadron Collider, LHC, recreate conditions that only exist naturally in the cores of neutron stars or in the first fractions of a second after the Big Bang. At CERN, the European Organisation for Nuclear Research, massive particles are accelerated along circular tracks at incredible speeds. In the LHC, lead ions, nuclei of heavy atoms stripped of electrons, are hurtled toward each other at 99.9999991%, the speed of light. The collisions release energy densities so high that protons and neutrons melt into their quark components, creating a quark-gluon plasma for the briefest instant. It's in this fleeting state that strange quarks appear in higher numbers than they do in normal matter, giving physicists a window into the physics of strange matter. The RHIC in New York works in a similar way, colliding heavy ions like gold nuclei. When these collisions happen, temperatures reach trillions of degrees and the energy is so intense that quarks and gluons no longer remain confined within protons and neutrons. Instead, they move freely in a hot, dense soup. This is precisely the environment where strange matter could theoretically form. Detectors surrounding the collision point record thousands of particles flying out in every direction, capturing data on quarks, gluons, and the rare appearance of strange quarks. Scientists spend years analysing this data, looking for patterns that indicate the formation of short-lived droplets of strange matter, known as strangelets. Strangelets are incredibly small and incredibly elusive. They are not stable under everyday conditions, and in the lab, they exist for mere fractions of a second. Detecting them requires instruments capable of measuring particle mass, charge, energy, and trajectory with extreme precision. Magnetic spectrometers bend the paths of charged particles to separate them by mass and charge. Calorimeters measure their energy. Time-of-flight detectors track how fast particles travel across known distances. By combining all this data, physicists hope to spot the signature of a strangelet, a particle that is denser than normal nuclear matter, with unusual charge-to-mass ratios. Even with the most advanced detectors, strangelets are like needles in a cosmic haystack. In a single collision, millions of particles fly outward. Only a few may be strangelets, and they may decay almost instantly. The challenge is sorting through this torrent of data to identify anything unusual. Scientists use machine learning, pattern recognition, and statistical analysis to pick out candidates. Even then, no single detection is enough. Multiple experiments must observe the same behavior to confirm the existence of strangelets. Beyond colliders, scientists also search for strangelets in cosmic rays, the high-energy particles that constantly bombard Earth from space. Cosmic rays contain protons, atomic nuclei, and sometimes rare heavy particles. If strangelets are ejected from neutron star collisions or other extreme cosmic events, they could travel across the galaxy and enter Earth's atmosphere. Specialized detectors, often located in high-altitude observatories or deep underground labs, are designed to capture these rare visitors. Cosmic ray detectors work in clever ways. Some use layers of plastic scintillators, which light up when charged particles pass through, allowing scientists to measure the particles' energy and velocity. Others use supercooled detectors to capture particles without destroying them. When a strangelet passes through, it would interact differently than ordinary cosmic rays. It would be ultra-dense, slow for its mass, and possibly carry an unusual electric charge. Finding one would be like catching a tiny piece of a neutron star hurtling through space. Experiments in the lab and observations of cosmic rays complement each other. Colliders allow scientists to recreate the high-energy conditions that produce strange quarks and test the theoretical models in a controlled environment. Cosmic ray searches provide a natural experiment where strangelets may have already formed in extreme astrophysical events and survived the journey across space. Together, they cover both the creation and detection sides of the puzzle. Laboratory experiments also teach us about quark-gluon plasma, which is critical to understanding strange matter. This plasma is a state where quarks and gluons are no longer confined inside protons and neutrons. By studying it, scientists can observe how strange quarks behave, how they interact with up and down quarks, and under what conditions they can form stable configurations. The lifetime of these plasmas is extremely short, less than a trillionth of a second. But within that time, physicists can gather enough data to test models of quark interactions and stability. RHIC experiments have produced interesting results. By colliding gold nuclei at high energies, physicists have observed enhanced production of strange quarks, an essential condition for strange matter. While no long-lived strangelets have been confirmed, the results show that the basic ingredients can be created in the lab. These findings inform astrophysical models, suggesting that strange matter could naturally form in environments where density and pressure are extreme, such as neutron star interiors. The LHC has gone even further. Collisions of lead ions at unprecedented energies produce temperatures more than 100,000 times hotter than the centre of the Sun. Detectors like ALICE ATLAS and CMS capture data on thousands of particles per collision. ALICE, specifically designed to study quark-gluon plasma, measures particle yields, energy spectra, and strange quark production. These measurements are critical for testing the hypothesis that quark matter can organize itself into stranglets under high energy conditions. Beyond just creating strange quarks, these experiments help scientists understand how quarks combine and interact under extreme conditions. In normal matter, quarks are locked inside protons and neutrons. In the plasma, they move freely, collide, and occasionally form short-lived clusters. Some of these clusters may be proto-stranglets. By analysing their behaviour, physicists learn the rules that govern strange matter, how density, temperature, and quark content affect stability, and what properties a strangelet would need to survive. Searching for strangelets in cosmic rays is equally challenging. Earth's atmosphere absorbs most incoming particles, so detectors must be sensitive enough to detect rare events without being overwhelmed by background radiation. Balloon-based experiments rise to high altitudes to catch cosmic rays before they interact with the atmosphere. Satellite-based detectors orbit the Earth to measure cosmic ray composition directly in space. Ground-based observatories bury deep underground shield-sensitive equipment from interference, allowing detection of particles that penetrate deep into Earth. The signals physicists look for in cosmic rays are subtle but distinctive. Strangelets would move more slowly than ordinary nuclei of the same energy because they are denser. They might have unusual charge-to-mass ratios that don't match known atomic nuclei. They could also leave unique tracks in detectors, as their extreme density interacts differently with the sensor material. Every candidate event is scrutinized carefully, with scientists checking for statistical flukes, instrumental errors, or known particles that could mimic the signal. Collisions in the lab and cosmic ray observations are linked by theory. Models of quark-gluon plasma, strangelet formation, and strange matter stability predict what signals to look for in both settings. By comparing laboratory results with cosmic ray data, physicists hope to confirm that strangelets not only can exist, but may already be travelling through space. Each experiment refines the parameters: what size a strangelet could be, how long it might survive, and what conditions are necessary for its creation. The interplay between lab experiments and cosmic ray searches has led to a deeper understanding of how strange matter might form naturally. Extreme pressures, high densities, and high temperatures are all required. Neutron star interiors provide these conditions over long timescales. Collisions in particle accelerators provide them for fractions of a second. Cosmic rays test whether strangelets can survive long journeys. Together, these approaches allow scientists to explore strange matter from creation to detection. Even small pieces of strange matter are potentially revolutionary. Detecting a single strangelet would confirm decades of theoretical work, prove that quark matter can be stable beyond atomic nuclei, and reveal a new form of matter in the universe. The hunt and its challenges. Detecting strange matter is not like spotting a star in the night sky. It's more like trying to catch a single snowflake in a hurricane, a tiny, ultra-dense fragment that appears for just a moment before disappearing. The universe does not hand it over easily. Strangelets are rare, fleeting, and hidden among trillions of ordinary particles. Physicists have to build experiments that are precise, sensitive, and capable of detecting the almost impossible. The first challenge is rarity. Strange matter is not abundant in the universe. It only forms under extreme conditions, inside neutron stars, during violent stellar collisions, or in the heart of high-energy particle collisions. Even when the conditions are right, the creation of a strangelet is far from guaranteed. Most collisions produce ordinary nuclear fragments or quark-gluon plasma. that dissipates without forming stable strange matter. In cosmic rays, strangelets are like whispers among shouts, rare visitors from extreme environments. The likelihood of detecting one on Earth is extremely low, which is why experiments have to run continuously, sometimes for years, to catch a single candidate. Even when strange matter is created, it is fleeting. In laboratories like RHIC and the LHC, strangelets may exist for fractions of a second. That's shorter than the blink of an eye, far shorter than any human could perceive directly. Detectors must capture every bit of information instantaneously. Sensors measure energy, mass and charge in real time, recording thousands of events per second. Researchers then sift through mountains of data to identify patterns that could indicate a strangelet. It is like finding a single perfect drop of water in a raging river. Another challenge is extreme conditions. Strange matter exists only in high pressure, high density, and high temperature environments. Outside these environments, strangelets may decay, fragment, or lose their extreme properties. A strangelet ejected into space might survive for years, but one created in a laboratory has to be detected immediately before it breaks apart. This means that experiments must not only produce strangelets, but also measure them in the exact conditions where they remain intact. Timing, energy calibration, and precise control of collisions are all critical. Detectors themselves face limitations. Even the most advanced instruments can be overwhelmed by ordinary particles. A single heavy ion collision can produce tens of thousands of particles, most of which are protons, neutrons, and pions. Amid this flood, a strangelet would be tiny and subtle, often mimicking ordinary particles unless analysed carefully. Physicists must distinguish between anomalies caused by instrumentation and true signals of strange matter. Sophisticated algorithms, data filters, and simulations are essential to separate real candidates from noise. Cosmic ray detection has its own hurdles. Strangelets travelling through space face interactions with interstellar gas, magnetic fields, and radiation. By the time they reach Earth, many may have fragmented or slowed down, altering the signals scientists expect to detect. Observatories in balloons, satellites, or deep underground must be sensitive to these subtle variations. The detectors must distinguish between strangelets and other high-energy particles that may behave similarly. Every event is scrutinized for mass, velocity, charge, and energy patterns, looking for that unique signature. The size of strangelets adds another layer of difficulty. Some may be microscopic, smaller than an atomic nucleus. Others could be larger, but still far smaller than everyday objects. Tiny strangelets are easier to overlook because their interaction with detectors is minimal. Larger strangelets, while easier to detect, are even rarer. Researchers must design experiments capable of detecting a wide range of sizes, balancing sensitivity with the ability to filter out background noise. Even defining what to look for is challenging. Strangelets have unusual charge-to-mass ratios compared to ordinary nuclei, but the exact values depend on theoretical models. Different models predict different combinations of up, down, and strange quarks affecting density, charge, and stability. Scientists must consider multiple scenarios and search for any pattern that fits, while avoiding false positives. A single misinterpreted event could derail years of research or create excitement over a false signal. Another difficulty is the interaction with ordinary matter. Strangelets can, in theory, convert nearby nuclear matter into strange matter under extreme conditions. This potential is carefully studied in theory, but in practice it means that experiments must handle them with extreme caution. Detectors, shielding, and experimental design must ensure that strangelets, if produced, do not react in unexpected ways with equipment. This level of control adds another layer of complexity to the hunt. temperature and pressure sensitivity also complicate detection. Strange matter may only remain stable at high pressures or within dense quark-gluon plasma. Once the droplet cools or leaves the high-energy environment, it may decay or fragment. Colliders recreate extreme temperatures for fractions of a second, so the experiment must measure the Stranglets during that fleeting instant. Timing, synchronization, and ultra-fast detection electronics are critical. Even when a candidate is detected, verification is a long process. A single event is never enough. Stranglets must be observed repeatedly, in multiple experiments and under different conditions. Laboratory results are compared with cosmic ray observations. Theoretical models are updated to account for new findings. This iterative process ensures that only genuine strange matter detections are accepted. The rarity of the phenomenon means that researchers must be patient and persistent. Statistical uncertainty is another obstacle. Stranglets may appear similar to heavy nuclei in detectors, making it difficult to distinguish signal from background noise. Scientists use probability models, cross-referencing multiple detectors and events to ensure that what they see is consistent with theoretical predictions. A small statistical anomaly may hint at strange matter, but confirming it requires rigorous analysis and often years of data. Laboratories also face practical limitations. Colliders have a maximum energy and luminosity, which restricts how many strange quarks can be produced. Generating sufficient quark-gluon plasma to form stable Stranglets requires pushing instruments to their limits. Detectors must survive extreme radiation and temperature conditions, maintaining precision over thousands of collisions. Any degradation in sensors can reduce the chance of detecting the already rare particles. Cosmic ray searches face environmental challenges. Detectors in orbit must withstand radiation, temperature fluctuations, and space debris. Balloon experiments must survive high-altitude winds and extreme cold. Deep underground observatories must filter out background radiation from surrounding rock. Every layer of complexity increases the difficulty of capturing a tiny, ultra-dense particle travelling across space. Theoretical uncertainty is also a challenge. Models of strange matter vary. Different equations predict slightly different densities, stability ranges, and quark compositions. Some models suggest Stranglets might decay almost instantly. Others suggest they could travel through space intact for millions of years. Experiments must be designed to test a wide range of possibilities, which complicates both laboratory and cosmic observations. Collaboration is essential. No single laboratory or observatory can do it alone. Physicists from around the world share data, compare findings, and refine models together. CERN, RHIC, LHC, and cosmic ray observatories coordinate efforts to cover both creation and detection. Each experiment informs the next, gradually improving the search for strange matter, even if direct detection remains elusive. The hunt also pushes technology forward. Ultra-sensitive detectors, high-speed data processing, and advanced particle simulations all emerge from the need to detect Stranglets. Even without direct detection, these experiments expand human capability to study the universe at its most extreme. Strange matter may be rare, but the process of searching for it transforms science and technology. Even with these precautions, detecting strange matter remains one of the most difficult experiments in modern physics. Traces of strange matter in the stars. The search for strange matter doesn't stop in laboratories or particle colliders. Neutron stars, pulsars, and violent cosmic collisions all serve as natural laboratories where strange matter could form, survive, and even reveal itself through subtle clues. Unlike terrestrial experiments, these cosmic observatories offer conditions impossible to recreate on Earth. Pressures billions of times higher than anything we can produce. Densities where a single teaspoon of material could weigh 1 billion tons, and collisions that release unimaginable energy. Neutron stars are the most obvious suspects. They are born when massive stars explode in supernovae, leaving behind a dense core composed almost entirely of neutrons. But the conditions inside these stellar remnants are extreme enough that quarks may no longer remain confined to individual neutrons. In the core, pressure and density can crush neutrons so tightly that up, down, and strange quarks may mingle freely. This quark soup could, in theory, stabilize into strange matter, forming the heart of a strange star. Observers can't see inside, but subtle signatures, rotation speed, mass, radius, and emissions offer hints. One clue lies in the relationship between mass and radius of neutron stars. Standard models of neutron stars predict specific ranges for these values based on nuclear physics, but some stars appear heavier or smaller than expected, suggesting a denser core than ordinary neutron matter allows. Strange matter, with its self-binding and extreme density, could explain these anomalies. A neutron star with a strange matter core would be smaller for the same mass, its gravity stronger, its structure different. Measuring these deviations requires precise observations using X-ray telescopes and pulsar timing. Pulsars, rapidly spinning neutron stars that emit beams of radiation, like cosmic lighthouses, provide another window. Glitches, sudden changes in rotation speed, can reveal internal structure. In some pulsars, glitches are unusually small, frequent or patterned in ways that standard neutron star models struggle to explain. Strange matter cores could create a rigid, self-bound interior, altering how the star responds to rotational stress. By studying these tiny variations, astrophysicists can infer the presence of extreme forms of matter inside. Neutron star mergers are perhaps the most dramatic laboratories. When two neutron stars collide, they release massive amounts of energy, gravitational waves, and ejected matter. If one or both stars contain strange matter, some of that material could survive ejection, potentially forming strangelets. Observing the aftermath through gravitational wave detectors like LIGO and Virgo, and through electromagnetic observations across the spectrum, may reveal anomalies in mass, velocity, or radiation that hint at strange matter formation. The composition of ejected material, when it can be measured, may show heavier or denser fragments than ordinary nuclear matter would allow. Gravitational wave signals themselves can carry fingerprints of strange matter. The waves produced in a neutron star merger are influenced by the star's internal structure. Stars with strange matter cores behave differently under tidal forces than ordinary neutron stars. This affects the waveform detected by observatories on Earth. Physicists can compare the detected waveforms to models of both normal and strange matter stars. Small deviations could indicate that one or both of the merging stars contained quark matter in a strange configuration. Strange matter could also affect electromagnetic emissions from these events. X-rays, gamma rays, and neutrinos emitted during collisions carry information about density, temperature, and composition. If strange quarks are present, they could influence the cooling rate of the merged object, the energy distribution of emitted particles, or the dynamics of ejected matter. Observatories sensitive to multiple wavelengths, like the Chandra X-ray Observatory and Fermi Gamma Ray Space Telescope, help capture this information. Scientists analyze the timing, spectrum, and intensity of these emissions for signs of unusual density or matter composition. Pulsar mass measurements add another layer of evidence. Some neutron stars exceed the maximum mass predicted by standard nuclear physics, yet do not collapse into black holes. This hints at additional internal pressure, possibly from strange matter cores. Observatories using radio and X-ray telescopes measure pulsar masses through binary system dynamics. Deviations from expected mass limits suggest the presence of denser, self-bound matter inside the star. Strange matter provides a possible explanation. Its internal binding allows the star to support more mass without collapsing. The timing of pulsar emissions also offers clues. Millisecond pulsars, spinning hundreds of times per second, display remarkable rotational stability. Some exhibit sudden spin-ups or spin-downs, glitches that are difficult to explain with ordinary neutron star models. Strange matter cores, with their extreme rigidity and unique internal dynamics, could produce these anomalous behaviors. By analyzing the frequency, amplitude, and pattern of glitches across different pulsars, astrophysicists can search for consistency with theoretical predictions of strange matter interiors. Cosmic rays may carry hints of strange matter as well. Neutron star mergers eject matter at high speeds, and if strangelets survive the journey through space, they could reach Earth as ultra-dense cosmic particles. Detectors on satellites, high-altitude balloons, and underground labs are scanning for these rare visitors. A strangelet would behave differently than ordinary nuclei, moving slower for its mass, having unusual charge-to-mass ratios, and interacting with detectors in unexpected ways. Identifying such a particle would provide direct evidence that strange matter exists beyond theoretical models. Supernova remnants also offer indirect signs. When massive stars explode, the composition of the ejected material can hint at the state of matter inside the core. If the core contained strange matter or quark-gluon plasma, certain heavy elements may be overproduced, or the dynamics of the explosion may differ from predictions based on ordinary nuclear matter. Observatories measuring spectra, elemental abundance, and light curves can search for these subtle anomalies. Neutrinos, nearly massless particles produced in enormous quantities during supernovae and neutron star mergers, provide another clue. Their energy spectrum, timing, and flux depend on the conditions inside the star. Strange matter cores could alter neutrino production or propagation, leaving detectable signals for neutrino observatories like Super Kamiokande or IceCube. These elusive particles carry information from deep within dense stars, offering a rare glimpse into matter at extreme densities. Observing strange matter in astrophysics is a combination of patience, technology, and theory. Each dataset, gravitational waves, X-rays, gamma rays, pulsar timing, neutrino flux, offers a piece of the puzzle. Scientists compare observations to predictions from quark matter models, looking for consistencies that point to strange matter. Even a single observation consistent with these models can guide laboratory experiments, helping refine conditions to produce strangelets and study their properties. The universe provides extreme natural laboratories that no collider on Earth can match. Neutron star interiors, mergers, and supernova cores offer pressures and densities billions of times higher than anything in human-made experiments. Observing the outcomes of these events through light, gravitational waves, or cosmic rays allows physicists to infer the presence of strange matter indirectly. Every observation, no matter how subtle, is a potential clue. Strange matter's fingerprints are subtle but pervasive. Mass radius anomalies, rotational glitches, tidal deformability in mergers, unusual neutrino fluxes, and cosmic ray particles all carry potential signals. By combining data across multiple messengers, scientists build a case for the presence of strange matter without ever touching it directly. These observations complement laboratory searches, offering a broader perspective on where and how strange matter exists. Even extreme events like neutron star black hole collisions may reveal strange matter. If a neutron star with a strange matter core is disrupted by a black hole, the ejected material could contain ultra-dense fragments, providing opportunities for detection in both gravitational waves and electromagnetic emissions. Modelling these events helps predict what signals to look for, guiding telescopes and observatories to the right times and locations. Strange matter is one of the most extreme substances physicists have ever imagined, and naturally people have wondered, could it be dangerous if it touched Earth? Movies love to play with the idea. A tiny particle from a collider, a Stranglets, suddenly spreading across the planet, converting everything into ultra-dense, indestructible matter. It's thrilling for storytelling, but scientists have analysed these fears carefully. Particle colliders like CERN's LHC push matter to extreme energies, but still nowhere near the pressures and densities inside neutron stars where strange matter could survive. Even if a strangelet were created, it would be so tiny and short-lived that it would decay before touching ordinary atoms, making doomsday scenarios practically impossible. Cosmic rays constantly bombard Earth with energies far greater than any human-made experiment. Yet the planet remains intact, which is the universe's own proof that strangelets can't trigger runaway destruction. Scientists ran detailed simulations, modelled interactions at the quark level, and compared results with astronomical observations, and all point to the same thing. Strange matter is exotic, fascinating, but safe here on Earth. The story of strange matter isn't just about what might happen, it's about what it already does in the universe. Neutron stars, born from the remnants of supernovae, squeeze matter to such extremes that neutrons themselves may break apart into their constituent quarks. If strange quarks join up and form strange matter, these stars could become strange stars, denser and more rigid than ordinary neutron stars. Their behaviour, their rotation, mass, radius, and the way they ripple space-time during collisions could reveal their hidden cause. Observatories detect gravitational waves, X-rays, gamma rays, and even neutrinos to probe these extreme interiors. When neutron stars collide, the debris, energy, and radiation could carry traces of strange matter into space, providing clues we can detect here on Earth. Some researchers speculate that strange matter might even be connected to dark matter. It's a compelling thought. Dark matter is invisible, makes up most of the universe's mass, and only interacts weakly with ordinary matter. Strangelets travelling through space would be ultra-dense but difficult to detect, and in principle, a population of small, stable strange matter fragments could contribute to the unseen mass that binds galaxies together. It's purely theoretical, but it shows how studying strange matter could rewrite our understanding of the cosmos and the fundamental composition of everything in it. Understanding strange matter also teaches us about quantum chromodynamics, QCD, the theory describing how quarks interact via the strong nuclear force. Extreme densities in strange matter test QCD in ways ordinary atoms never could. Studying phase transitions from ordinary nuclear matter to quark matter to strange matter helps physicists explore the limits of physics itself. Each experiment, observation, and simulation is a step toward mapping matter at its ultimate extremes. Many questions remain open. Could strange matter be stable at room temperature, or does it need extreme pressures to hold together? Are there strange stars out there in our galaxy, quietly spinning as cosmic lighthouses, waiting for us to confirm their existence? Future missions and experiments like NICA, gravitational wave observatories, LIGO Virgo Cagra, and next-generation colliders are designed to probe these mysteries. Every new measurement could reshape our understanding of how matter behaves when pushed beyond everything we experience on Earth.